Imagine gazing into the night sky, that eternal canopy scattered with countless stars, and asking yourself the question that has haunted humanity for centuries. What lies beyond the farthest reaches of the cosmos? For millennia, the edge of the universe has captivated the imagination, provoking both wonder and perplexity. It is a concept that not only stretches the limits of what we know, but also challenges the very framework through which we define existence. And now, with the aid of groundbreaking technology and bold theoretical exploration, science is inching closer to answers once thought beyond reach. Yet this journey is not straightforward. It is a path carved through layers of complexity, where mathematics, physics, and observational astronomy converge to illuminate the unknown. Researchers are diving deeper than ever into the fabric of the universe, confronting some of the most difficult questions in modern science. Is there an edge to the universe? And if so, what lies beyond it? The idea of a boundary, a place where the universe simply stops, is deeply counterintuitive. According to our current understanding, the universe is expanding, a phenomenon akin to the surface of an inflating balloon. Every point on this surface moves away from every other point, and the farther something is, the faster it recedes. But this expansion does not imply an edge in the traditional sense. There is no cosmic wall, no curtain we might peek behind. Instead, the universe could be either infinite or finite, but without a boundary, much like the surface of a sphere where one can travel indefinitely without ever encountering a sharp edge. This analogy becomes especially intriguing when paired with our modern observational tools. With the most powerful telescopes, we are peering into deep space and seeing light that has journeyed billions of years to reach us. In doing so, we are not just looking far away, we are looking back in time into the early chapters of the universe's story. What we call the observable universe is this vast sphere of ancient light, a cosmic bubble with Earth at the center, not because we are special, but because we are observing from here. However, there are profound limits to what we can detect. The cosmic horizon, the ultimate edge of our observational reach, is defined by the distance light has traveled since the beginning of the universe, roughly 13.8 billion years ago. Due to the expansion of space itself, this observable sphere now spans about 93 billion light years in diameter. But what lies beyond this horizon remains hidden. Not because it doesn't exist, but because light from those distant regions hasn't had time to reach us, and may never, thanks to the universe's accelerating expansion. Some theories suggest these unreachable regions may hold vast stretches of space similar to ours, or perhaps domains governed by different physical laws altogether. In this context, the edge of the universe is not a place, but a boundary of knowledge. It marks the dividing line between what we can observe and what remains forever concealed. The implications of this boundary are staggering. It not only defines the scale of the cosmos, but also stirs deep philosophical questions. Are we a tiny pocket in an infinite expanse, one bubble in a cosmic foam of universes? Could the universe wrap around itself, forming a closed loop where traveling far enough in one direction eventually brings you home? These questions draw us into the realm of theoretical physics, where concepts like multiverses, higher dimensions, and cosmic topology are explored not just as science fiction, but as serious possibilities. Our quest to comprehend the universe's boundaries is inseparable from our desire to understand its origins, its structure, and ultimately, our place within it. Historically, humanity's grasp of cosmic scale has grown in bursts of enlightenment. In antiquity, the heavens were thought to rotate around a stationary Earth, with the stars affixed to a celestial sphere. This Earth-centered view prevailed until thinkers of the Renaissance, such as Copernicus and Galileo, radically redefined the cosmos. They revealed that Earth orbits the Sun, and the stars were distant suns scattered throughout space. The invention of the telescope opened up entire new realms. Galileo saw moons orbiting Jupiter, challenging the idea that everything revolved around Earth. Kepler uncovered the laws of planetary motion, and later the structure of the Milky Way began to emerge. Then, in the early 20th century, Edwin Hubble shattered yet another boundary. Our galaxy was not the entire universe. It was just one among countless others. Even more astonishing, those galaxies were not static. They were moving away from us. The universe was expanding. This revelation transformed cosmology. the Big Bang Theory emerged, describing a universe that had a beginning and has been growing ever since. With space telescopes and sensitive detectors, we now see deeper and farther than ever before. The cosmic microwave background, a faint afterglow of the Big Bang, offers a snapshot of the universe when it was just 380,000 years old. Today, we know that there are likely more than 2 trillion galaxies, each containing billions of stars. And still, we've only seen a sliver. We live in a universe that is far larger, stranger, and more dynamic than we once dared imagine. Its boundaries, if they exist at all, are not physical walls but conceptual thresholds. They are defined not by where space ends, but by the limits of our perception and the ever-evolving scope of our understanding. As we continue to explore, to question, and to innovate, the edge of the universe remains one of the most profound frontiers in science. Not a conclusion, but a beginning. An invitation to wonder and to discover what still lies beyond. And yet scientists do not confine their curiosity to the visible structure of the cosmos. Beyond the familiar stars and galaxies lies a more elusive frontier, the unseen forces shaping the very fabric of the universe. Dark matter and dark energy, two phenomena that remain largely mysterious, are believed to comprise the vast majority of the universe's mass energy content. These forces do not emit, absorb, or reflect light, yet their gravitational fingerprints are unmistakable. It is through their subtle influence on cosmic motion and expansion that we begin to glimpse their presence. Our evolving perception of the universe is not static. As theories develop and evidence accumulates, new ideas emerge. Some that once seemed outlandish are now serious contenders for truth. Concepts like the multiverse suggest our universe may be just one of many, each governed by its own laws of physics. If true, it challenges the very foundation of what we consider reality. The notion that there could be realms entirely beyond our observational reach is no longer reserved for science fiction. With every discovery, we are reminded that the boundary between the known and the unknown is fluid, continuously pushed outward. This quest to understand our cosmic surroundings is deeply human. It's not only about mapping the stars or charting galaxies, it's about situating ourselves in the grand narrative of existence. The farther we look, the more profound the questions become. What is our place in this vast arena? Are we alone? Is there a boundary to the universe, or is it infinite? To even begin answering these questions, scientists depend on an arsenal of extraordinary tools and technologies. Chief among them is the telescope, a centuries-old invention now evolved into a sophisticated eye trained on the farthest reaches of space. Optical telescopes capture visible light from stars and galaxies, enabling us to peer across light years with striking clarity. Radio telescopes, in contrast, tune into frequencies invisible to the human eye, decoding signals that pass effortlessly through cosmic dust and darkness. Orbiting high above Earth's atmosphere, space-based observatories like the Hubble Space Telescope deliver breathtaking images free from atmospheric interference. These instruments capture light across a vast range of wavelengths, from ultraviolet to infrared, revealing details of star formation, galactic collisions, and exoplanetary atmospheres. They uncover events that occurred billions of years ago, essentially allowing us to peer back in time. Spectroscopy, another cornerstone of modern astronomy, breaks down starlight into its spectral components. Each element leaves a unique signature in this light, enabling researchers to determine the chemical composition, temperature, and motion of celestial bodies. When a galaxy's light shifts toward the red or blue end of the spectrum, scientists can measure how fast it is moving and in which direction, crucial information for understanding cosmic expansion. Space probes and rovers extend this exploration to our own solar system and beyond. These robotic emissaries are equipped to endure the harshest environments, from the surface of Mars to the icy moons of Jupiter. They gather data on planetary geology, weather, and potential for life, sending back volumes of information that no telescope could collect alone. Gravitational wave detectors, a recent leap in scientific capability, offer a completely different mode of observation. Rather than using light, they sense the ripples in spacetime caused by colossal events like merging black holes. These waves travel through the universe largely unimpeded, bringing us direct evidence of cataclysmic phenomena that might otherwise remain invisible. In doing so, they expand our perception into an entirely new dimension. Together, these tools form an interconnected framework, a multi-layered approach to decoding the universe. Each technology contributes a unique piece of the puzzle, offering insights not only into the structure of the cosmos, but also into its origins, evolution, and fate. Measuring distances in this vast expanse presents its own challenges. Unlike terrestrial navigation, where fixed landmarks provide orientation, cosmic measurement relies on more abstract methods. For nearby stars, astronomers use parallax. This technique is similar to holding your finger in front of your face and watching it appear to shift as you alternate closing each eye. By observing the same star from two different positions in Earth's orbit, scientists can triangulate its distance using basic geometry. When distances extend beyond what parallax can measure, astronomers turn to standard candles, objects whose intrinsic brightness is well known. A prime example is the Type 1a supernova, an exploding star that shines with a predictable luminosity. By comparing its known brightness to how bright it appears from Earth, astronomers calculate how far its light has traveled. For truly immense scales, redshift becomes the primary metric. As galaxies move away from us, the light they emit stretches into longer wavelengths, shifting toward the red end of the spectrum. This shift isn't just a curiosity, it's a key to understanding the expanding universe. The greater the redshift, the faster a galaxy is receding and the farther away it is. This phenomenon led to one of the most profound discoveries in cosmology, Hubble's law. It states that the farther a galaxy is from us, the faster it appears to be moving away. It's as if space itself is expanding, carrying galaxies with it like raisins in rising dough. This observation supports the idea that the universe had a beginning, often described as the Big Bang, and has been growing ever since. The concept of redshift acts as a cosmic signal flare, pointing to an ever-changing universe. Its implications reach far beyond mere distance measurement. It provides the scaffolding upon which we build our models of cosmic history, helping estimate the universe's age and offering insights into the elusive force known as dark energy, believed to be accelerating the expansion. To visualize this, picture a balloon with dots scattered across its surface. As the balloon inflates, each dot moves away from the others, not because it is moving on its own, but because the surface itself is stretching. In the same way, galaxies drift apart, not through independent motion, but through the expansion of the very fabric of space. This revelation challenges earlier assumptions of a static universe. In that old model, space was eternal and unchanging, a cosmic stage set once and for all. But the evidence now suggests a far more dynamic story, one of birth, change, and unceasing motion. The universe, it turns out, is not a frozen tableau, but an unfolding drama, one we are only beginning to understand. However, this idea struggles to account for certain observable phenomena that speak loudly of a universe in motion. Chief among them is the increasing distance between galaxies, as well as the presence of the cosmic microwave background radiation, both of which are compelling indicators that the universe is not static, but evolving. These features directly contradict the notion of an unchanging cosmos. Instead, they point to a dynamic, restless universe, one that is unfolding through time, shaped by cosmic events and governed by change. The theory of an expanding universe stands in stark opposition to the timeless stillness of the static model. It offers a view not of eternal stasis, but of a cosmos alive with motion, history, and transformation. This shift in understanding has redefined our place in the universe. The evidence supporting the expanding universe, meticulously gathered through observation and calculation, has transformed modern cosmology. No longer do we imagine the universe as fixed or eternal. Instead, we now see it as a vast, intricate story still being written. From this view emerges the Big Bang theory, a framework that suggests everything we know, from the smallest atom to the largest galaxy, began from an unimaginably hot and dense origin. Proposed in the early 20th century, the Big Bang theory paints a revolutionary picture that the universe was once compact beyond comprehension, then rapidly expanded, stretching space itself. It is not merely the movement of objects through space, but space itself that is growing. To imagine this, picture a balloon being inflated. As it expands, dots on the balloon's surface move apart, not because they are traveling across the surface, but because the surface itself is stretching. In this way, galaxies are not flying away through static space, rather they are being carried by the swelling fabric of the universe. This ongoing expansion gives us a natural limit, not to the universe itself, but to what we can observe. When we look into the night sky, we are peering into the past. Light from distant galaxies travels across immense distances to reach our eyes. The farther the source, the older the light, which means we are effectively looking back in time. But there is a boundary to this backward gaze. Beyond a certain distance, light has not had enough time to reach us since the Big Bang. This horizon defines the observable universe. What lies beyond this edge? It is one of the most tantalizing questions in science. Though we cannot see it, the logic of expansion suggests that there is more, much more, that remains hidden. These unseen regions may hold new structures, new physics, or even entire realms with properties vastly different from our own. Could there be other bubbles of space-time, each governed by its own rules? The pursuit of these questions has propelled astrophysics into thrilling new territory. This cosmic curiosity extends to other profound mysteries, like dark matter and dark energy. Together, they appear to make up the vast majority of the universe, yet they resist direct detection. Dark matter reveals itself only through its gravitational influence, helping to shape galaxies and maintain their integrity. Dark energy, even more elusive, is believed to drive the accelerating expansion of the universe. These enigmatic forces push the boundaries of what we can know, urging scientists to explore deeper. To begin to grasp the nature of the observable universe, we must first look at its composition. At its foundation lies an intricate web of galaxies, enormous structures made of stars, gas, dust, and dark matter. A single galaxy may contain millions or even trillions of stars, each born in clouds of gas, living out luminous lifespans, and ending, often dramatically, in supernovae. These stellar explosions scatter heavy elements across space, seeding new generations of stars and planets. Within these galaxies are planetary systems, like our own solar system. Orbiting stars, these systems include a wide array of celestial bodies, planets, moons, asteroids, and comets. Some planets may lie within habitable zones where conditions could allow life to emerge. The study of these worlds has become a central quest in astronomy, as we seek not only to understand the universe, but to find our place within it. And throughout all of space, faint but ever-present, is the cosmic microwave background radiation. This ancient light is the echo of the Big Bang, a relic from a time when the universe was just 380,000 years old. Today, it fills the cosmos uniformly, whispering secrets of the early universe and providing scientists with crucial insights into its origin, age, and development. All these discoveries shape a profound truth. The universe is not static, not fixed. It is evolving, expanding, and teeming with phenomena that stretch the imagination. And while much remains unseen, each new revelation draws back the curtain just a little more, inviting us to keep exploring the cosmos and ourselves. And lastly, we cannot forget about the immense, seemingly barren expanses between galaxies, the vast, silent territories known as cosmic voids. These immense regions, which appear almost completely empty, are not simply the absence of galaxies. Rather, they are fundamental to the architecture of the universe. Like the negative space in a grand painting, they help define the form and flow of everything around them. Though largely devoid of matter, cosmic voids offer critical clues about the distribution of mass and energy across the cosmos. They are integral to the vast scaffolding upon which galaxies, stars, and planetary systems are built. When taken together, galaxies, stars, planets, dark matter, cosmic radiation, and these immense voids, the universe begins to reveal itself as a vast, interconnected fabric. This fabric is not static. It moves, it pulses, and it evolves. It is in this dynamic interplay of cosmic elements that the story of our universe is written. Through this ceaseless interaction, we inch closer to understanding where we come from, how we came to be, and where we might be headed. Dark matter and dark energy are two of the most puzzling and foundational components of this story. They are invisible forces operating in the background, shaping everything while evading direct detection. Their nature is not fully understood, yet their influence is unmistakable. Dark matter makes up a significant portion of the universe's total mass. It behaves like a cosmic adhesive, an invisible glue binding galaxies together. But it is not dark in the usual sense, nor is it matter as we typically understand it. It neither emits, absorbs, nor reflects light. It cannot be seen. Scientists infer its presence only through its gravitational effects, the unseen hand shaping the motion of stars and galaxies, sculpting the universe into the structures we observe. Dark energy, on the other hand, is the mysterious force believed to permeate all of space. It is the driving power behind the universe's accelerated expansion. While dark matter pulls structures together, dark energy pushes them apart. This cosmic tug-of-war between attraction and repulsion defines much of what we observe on the grandest scales. It is a quiet, persistent force working against gravity and winning. As we approach the outermost reaches of the universe, the influence of these forces becomes especially pronounced. Dark matter shapes the cosmic web, a vast three-dimensional network of filaments and voids. Within this web, dark matter gathers into dense regions, creating gravitational wells that trap ordinary matter and give rise to galaxies and galaxy clusters. These structures are the fingerprints of dark matter across the cosmos. Meanwhile, dark energy plays a central role in determining the fate of the universe. As the cosmos expands, dark energy accelerates this expansion. Over immense time spans, galaxies are pushed farther apart, and the universe grows increasingly sparse. Eventually, the separation may reach such extremes that distant galaxies drift out of view, their light stretched and dimmed until it is no longer detectable. In this way, dark energy defines the limits of what we can observe, creating an ever-shifting horizon. This brings us to the concept of the cosmic horizon, the ultimate boundary of our observable universe. Picture standing on the deck of a ship, gazing out across a vast ocean. The horizon marks the farthest point you can see. Beyond that lies an expanse forever hidden from view. In the same way, the cosmic horizon marks the outer edge of what light has been able to reach us from the beginning of time. Because the universe has been expanding since the Big Bang, only so much light has had time to arrive. That distance defines our observable universe. The cosmic horizon is more than a limit. It is a profound marker of time and space. Beyond it, there are regions of the universe whose light will never reach Earth, no matter how long we wait. These regions are forever beyond our observational reach. They exist, but for us, they are unseeable. Yet, the cosmic horizon also provides a valuable tool. By studying what lies near its edge, especially the faint glow of the cosmic microwave background, scientists can peer into the early universe. This relic radiation is the afterglow of the Big Bang, a snapshot of the cosmos as it existed just a few 100,000 years after its birth. It carries the signatures of cosmic inflation, a period of mind-bogglingly rapid expansion that shaped the structure of everything that followed. Through it all, the dark matter that binds, the dark energy that drives apart, the voids that define, and the horizon that limits, we gain a deeper appreciation of our place in the cosmos. This intricate interplay of forces not only defines what we see today, but hints at the unseen, the unseeable, and the vast possibilities that stretch beyond the reach of light itself. And ultimately, the cosmic horizon stands as both a symbol and a limit, a silent, invisible boundary marking the furthest edge of what we can observe. It embodies the staggering immensity of space, but also the current boundaries of human understanding. Like a veil drawn across the distant universe, it challenges us to wonder what lies beyond, igniting our curiosity and pushing the frontiers of cosmological thought. Shortly after the Big Bang, something extraordinary happened. The universe, in its earliest moments, underwent a sudden and astonishing burst of growth known as inflation. This wasn't a slow, gradual expansion. It was explosive. Imagine blowing up a balloon in an instant, not just filling it with air, but causing the surface itself to stretch at an exponential rate. Except in this case, the balloon is space-time, and the expansion occurred in a fraction of a second, so small it defies intuition. During this infinitesimal sliver of time, the universe grew so rapidly that regions once adjacent were ripped apart and sent careening away from one another by incomprehensible distances. Picture two tiny points on the surface of a balloon, so close together they're nearly touching. Now imagine inflating that balloon until those same points lie oceans apart. This is the effect of cosmic inflation on the scale of the universe. One profound implication of this event lies in the cosmic microwave background radiation, the faint afterglow of the early universe. What we observe today as a near-uniform sea of ancient light once originated from tightly connected regions of space, but inflation threw them apart, scattering that light and stretching it across the heavens. This explains why the universe appears smooth and uniform when viewed from a distance, yet also contains astonishing variety. Galaxies, stars, clusters, voids, all born from subtle fluctuations in primordial matter. Inflation, then, is more than just a theory about size. It's a window into the birth of structure, the origin of complexity, and the reason we can look into the night sky and see order amid chaos. It provides a framework that accounts for both the immense scale of the universe and the intricate architecture of cosmic formations. But the observable universe, everything we can detect, measure, and interpret, is likely just a tiny island in a much grander ocean. Beyond our cosmic horizon lies a realm so vast and enigmatic that it defies not only observation, but imagination. Many scientists now propose that our universe may be one of less others, a single bubble in a vast cosmic foam. This concept, known as the multiverse, suggests a reality where each universe exists in its own space, with its own physical laws, constants, and even dimensions. In some versions of the multiverse theory, these parallel universes might be forever out of reach, separated from ours by distances or conditions that render interaction impossible. Others imagine collisions or branching paths, where new universes are constantly being born. If true, it would mean our cosmos is just one expression of an almost limitless variety of possible realities. Another possibility envisions the universe as infinite, continuing endlessly in all directions. In this model, the observable universe is but a grain of sand on an endless beach. Beyond what we can see, galaxies and structures could stretch on forever, never repeating yet never ending. Every time we think we've reached the edge, it's merely the edge of our view, not the edge of existence. Some theories go even further, suggesting that space and time themselves may be curved or folded. In such a universe, traveling far enough in one direction might eventually bring you back to where you started, like walking a great circle around the surface of a sphere. There would be no true edge, no boundary, no outside, only a continuous, self-contained expanse. These ideas are not science fiction. They are built on the same mathematical rigor and observational evidence that brought us to understand black holes, dark energy, and gravitational waves, and yet they remind us how little we still know. The cosmos, in all its grandeur, is not merely a place, but a journey, a mystery that grows deeper the more we explore. And yet there is the compelling theory of cosmic inflation. It suggests that in the tiniest fraction of a second after the Big Bang, the universe experienced an unimaginably rapid and exponential expansion. This brief but explosive burst of growth would have stretched space itself, flinging regions that were once connected far beyond the limits of our current observational reach. What was once nearby has become eternally out of sight. The inflationary period didn't just shape the universe we observe. It may have pushed vast portions of the cosmos into darkness, regions we can never explore with our instruments. In those hidden expanses may lie the echoes of our own origin, or perhaps entirely new beginnings. These ideas open thrilling doors, portals into the unseeable, the unknowable. Though definitive answers remain just out of grasp, theories like these compel scientists to press on, to peer deeper into space, to ask grander questions. They push the boundaries not only of the observable universe, but of human imagination itself. Multiverse theories emerge from this same wellspring of inquiry. They offer a perspective so vast it challenges the very meaning of existence. To begin understanding, imagine standing at the edge of everything, the edge of the observable universe. Traditionally, this boundary is marked by the cosmic microwave background, or CMB, a faint afterglow from the Big Bang. Beyond that, it seems, only darkness remains. But is that truly the end? Multiverse theories argue that it isn't. Instead, they suggest that what we call the universe may be only one bubble in an immense cosmic sea. Picture a boundless ocean, each bubble within it a universe of its own, floating alongside countless others. Each of these universes could operate under entirely different physical laws, harboring alternate realities shaped by varying conditions from their earliest moments. Ours may be just one chapter in a sprawling book of infinite tales. In this framework, the edge of our universe is not a wall, but a horizon. It is simply the boundary of what we can perceive. Beyond it, new realms may unfold, realms we may never witness directly, but which nonetheless could exist as vividly as our own. Cosmic inflation again takes center stage here. According to this theory, the same rapid expansion that gave rise to our universe may also have sparked others in a cascading process of universe creation. Each new universe forms with its own variations in temperature, density, and structure. These differences, though slight at birth, could produce radically divergent outcomes. Some of these universes might be teeming with matter and life. Others might collapse moments after forming. Each possibility is a brushstroke in a grander cosmic mural. Such ideas redefine the meaning of a boundary. If our universe is one among many, then its limits are not edges, but transitions. The boundary is less like a wall and more like a shoreline, one that meets a vast ocean whose depths remain uncharted. The story of our cosmos is written in light, and nowhere is this more evident than in the cosmic microwave background. Think of the universe just after the Big Bang, some 380,000 years into its existence. At that time, the cosmos was a scorching, dense fog of particles. Light could not travel freely. Photons, the particles of light, scattered endlessly off charged particles like electrons and protons. The universe was opaque, but as it expanded, it cooled. Temperatures dropped low enough for electrons and protons to combine, forming neutral hydrogen atoms. This transformation made space transparent for the first time. Light was released, light that had been trapped for hundreds of thousands of years. That light has traveled ever since, stretching and cooling as the universe expanded, shifting into microwave wavelengths. Today, we detect this ancient light as the CMB. It is a faint, nearly uniform glow that fills the sky, a whisper from the infant universe. When we observe it, we are not just looking at light, we are looking back in time. We are capturing a snapshot of the cosmos in its infancy, and within this glow, tiny irregularities reveal themselves. These fluctuations, minuscule variations in temperature and density, are the seeds from which galaxies, stars, and clusters would eventually grow. They are the original fingerprints of cosmic structure. By analyzing them, scientists can reconstruct a map of how matter was distributed in the early universe, how it clumped, how it evolved. Through this lens, the CMB becomes more than background noise. It is a blueprint, a silent witness to the birth of everything. It offers clues not just to the structure of our universe, but also to the mystery of its limits. Each pixel of data, each whisper of ancient light, is a step closer to understanding whether our universe is alone or one among an infinite chorus. Furthermore, the cosmic microwave background, or CMB, acts as a kind of boundary, a veil that defines the furthest edge of what we can observe in the universe. It marks the limit beyond which our instruments, no matter how powerful, cannot extract meaningful information. Light from those regions, tucked away in the unobservable depths of space, has simply not had enough time to reach us since the birth of the cosmos nearly 13.8 billion years ago. In this sense, the CMB is more than just a relic of a long-gone era. It is the backdrop of creation, the fossil radiation from a time when the universe transitioned from opaque plasma to transparent light, and it sets an undeniable physical constraint on our knowledge. We cannot see past it. We cannot reach beyond it. The universe, as far as we are concerned, ends there, not with a wall, but with a silence that has yet to be broken. Yet wormholes throw a wrench into that boundary. They defy the conventional image of a steadily expanding universe, an image where galaxies drift apart like embers from a dying fire carried on the winds of time and space. In our standard view, there are no true edges to the universe, only regions so distant that their light has not had enough time to arrive. But wormholes, theoretical bridges through space-time, offer a different kind of passage. They suggest the possibility of shortcuts, tunnels that connect far-flung parts of the universe, or perhaps even different universes altogether. Imagine folding space like a sheet of paper and poking a hole straight through. What once seemed impossibly far might become near in an instant. If wormholes can exist, then what does distance truly mean? And what becomes of the edges of our universe if they can be pierced or bypassed entirely? The idea is radical. Our understanding of space is grounded in the limitation imposed by the speed of light, a cosmic speed limit that ensures causality and maintains the order of events. But wormholes challenge that rule. They hint at a deeper architecture, a hidden scaffolding that allows for instantaneous travel across vast gulfs of space and perhaps time. This raises fundamental questions. Could wormholes allow communication or even travel to places beyond our cosmic horizon? If so, the CMB would no longer be a hard boundary, but just another point along a far more complex map. The implications ripple outward. Causality might break down, paradoxes could emerge, and our grasp on what is real may blur. These are not just thought experiments, they are cracks in the structure of contemporary physics, fissures that invite us to rebuild our theories from the foundation up. Just as wormholes challenge our sense of space, the notion of parallel universes stretches our concept of reality. Picture a vast multiverse, an endless cascade of realities where every choice, every quantum fluctuation spawns an alternate version of events. In one universe, you chose left, in another, right. These countless branches each follow their own paths, unfolding according to physical laws that may resemble ours, or diverge completely. With parallel universes, we confront the limits of our own assumptions. What if time flows differently in another universe? What if gravity is stronger or doesn't exist at all? If alternate realities operate under different laws, then how universal are the laws of physics we've come to rely on? Perhaps they are local truths, true only within the confines of our particular bubble of reality. The multiverse suggests that what we call impossible might simply be improbable somewhere else. It also casts our discoveries in a new light. If scientific truths differ across realities, then knowledge itself becomes layered. Each universe holding its own version of physics, its own insights, its own boundaries. Our universe might not be the rule, but the exception, one note in a cosmic symphony. And that realization transforms the way we approach science, not as the pursuit of a single truth, but as a journey through an ever-expanding field of possibilities. This brings us to the concept of extra dimensions, a cornerstone of many modern physical theories. We experience the world in three spatial dimensions: length, width, and height. But what if that's only part of the story? Advanced theories like string theory propose the existence of additional spatial dimensions beyond our perception, tightly curled into shapes far smaller than any particle detector can currently observe. According to these models, the universe isn't made up of point-like particles, but of infinitesimal vibrating strings. The specific ways these strings vibrate, what frequencies, what patterns, depend on the geometry of the extra dimensions that cradle them. These hidden dimensions shape the properties of particles, their mass, their charge, even their interactions with forces like gravity. And here lies another mystery. Gravity, the weakest of the four known fundamental forces, may feel diluted in our universe precisely because it leaks into these additional dimensions. What appears feeble to us might be immense elsewhere. If true, this would explain one of the most persistent puzzles in physics and unlock entirely new ways of understanding the cosmos. The existence of extra dimensions, like wormholes and parallel universes, doesn't just expand the map of the universe. It changes the rules by which the map is drawn. It asks us to look beyond the edges of our senses, beyond the visible, beyond even the comprehensible. It calls for imagination tethered to rigor, for curiosity tempered with skepticism. These ideas force us to reimagine space, time, matter, and meaning, not as fixed concepts, but as pieces of a deeper, stranger reality just beyond the veil of what we can see. Furthermore, the shape of the universe might be influenced by these dimensions, potentially giving rise to a far more intricate and multi-layered structure than the flat or curved spaces we typically imagine. These extra dimensions aren't just abstract mathematical curiosities. They're tools physicists use to confront some of the most profound questions about existence. They help us probe the earliest moments after the birth of the universe, peer into the enigmatic depths of black holes, and search for a bridge between the seemingly incompatible frameworks of quantum mechanics and general relativity. Rather than limiting our perspective, extra dimensions expand the stage on which the cosmic drama unfolds. They provide an enriched framework in which the four known fundamental forces, gravity, electromagnetism, and the two nuclear forces, might ultimately unite. Within this expanded canvas, physicists are not just drawing new boundaries, they are redrawing the very blueprint of reality. Brain cosmology presents a compelling reimagining of the universe's fundamental structure. It proposes that what we perceive as our universe, a vast expanse with 3 dimensions of space and 1 of time, might actually be a membrane or brain floating within a higher dimensional space known as the bulk. Picture a thin sheet drifting within a vast invisible ocean. That sheet is our universe. All we know and observe, the galaxies, stars, planets, even light itself, exists on this brain. Now imagine the edge of the universe not as a rigid wall or a final frontier, but as a soft threshold, a dynamic zone where our brain might brush against other brains or interact with additional dimensions. At this edge, the laws of physics may shift, ripple, or even rupture under the influence of higher dimensional forces. This isn't just theoretical musing. Such interactions could generate energy bursts, spark the birth of new universes, or trigger dramatic events. Perhaps even the Big Bang itself, a collision between brains echoing across cosmic history. Incorporating higher dimensions into our models transforms our conception of cosmic boundaries. The edge becomes not an end, but a gateway, a transition zone, teeming with potential, hinting at an interconnected multiverse whose implications are only beginning to surface. It challenges the notion of separation and finality, replacing it with fluidity, motion, and unseen connections. Cosmic topology takes this journey further by asking a deceptively simple question. What is the shape of the universe? Is it infinite, or does it loop back on itself? When cosmologists explore topology, they aren't just charting territory, they're mapping the rules of connection, how the universe is woven together on the grandest scale. One possibility is a flat, endless expanse where you could travel in any direction forever without encountering a border. Another is a finite universe, curved like the surface of a sphere. In that case, you could journey in a straight line and eventually find yourself back where you started without ever hitting an edge. There are even more exotic models, toroidal structures shaped like cosmic donuts or multidimensional manifolds twisted and folded beyond visual comprehension. These shapes aren't merely abstract concepts. They determine how the universe evolves, how galaxies cluster, and how light travels across space. If the universe is finite yet unbounded, what lies beyond what we can see? Is there even a beyond? These questions aren't philosophical speculation. They're rooted in observations, mathematics, and physical law. Both cosmic topology and our understanding of the universe's expansion play crucial roles in deciphering its ultimate destiny. Will everything continue to spread outward in an eternal drift? Will gravity eventually pull it all back together in a cataclysmic collapse? Or is there a delicate balance, an eternal state where expansion neither accelerates nor halts? Peering into these cosmic questions demands a view from the farthest reaches of space, but observing the edge of the universe is no easy task. The challenges begin with distance. The light that reaches us from the edge of the observable universe has been traveling for billions of years. When we look in that direction, we are not seeing the universe as it is. We are seeing it as it was, long before our solar system even formed. Technology places further limits on our vision. Telescopes must be exquisitely calibrated, and not all types of light, such as infrared or ultraviolet, can pass through Earth's atmosphere. To get a clearer picture, astronomers must place instruments in orbit, high above atmospheric interference. But launching and maintaining space telescopes is costly and complex, requiring immense coordination and resources. Even so, we press forward. Driven by the promise of answers, we build better instruments, expand our theoretical frameworks, and reach farther into the cosmos. What we find at the edge of the observable universe may one day redefine the edge of human understanding itself. Furthermore, the expansion of the universe adds a profound layer of complexity to our understanding of the cosmos. The universe is not a fixed, motionless entity. It is constantly stretching outward, like a balloon inflating in every direction. This ongoing expansion causes the light from distant galaxies and celestial objects to stretch as well, leading to what scientists call redshift. Redshift shifts light toward the longer, redder wavelengths of the spectrum, making those distant sources harder to observe. It's not just a matter of distance, it's a distortion of the very signals we rely on to understand what's out there. To compensate, Astronomers must employ highly advanced technologies and develop increasingly refined techniques to interpret these redshifted signals and reconstruct a clearer image of the distant universe. Yet, even with these tools, our grasp of the cosmos remains incomplete. Fundamental elements of our universe, dark matter and dark energy, continue to elude definitive explanation. These mysterious forces are thought to make up the vast majority of the universe's mass energy content, yet they remain largely theoretical, inferred through indirect observation and gravitational effects. This incomplete framework introduces deep uncertainties when we try to peer into the farthest reaches of space. What we know is dwarfed by what we don't. These unknowns complicate every measurement, every conclusion, and force us to approach the edge of the universe with humility and caution. Cosmic phenomena such as black holes deepen this enigma. They are not just astronomical curiosities, they are profound challenges to everything we think we understand about the laws of physics. To visualize a black hole, imagine a region in space where gravity is so intense that nothing, not even light, can escape its pull. This defines the event horizon, a kind of cosmic point of no return. Once matter crosses this invisible boundary, it vanishes from the observable universe, taking with it all information about its past state. The implications of this are staggering. If information is truly lost, it violates some of our most cherished physical laws. It calls into question the permanence and predictability of the universe itself. We often envision space as a boundless, if comprehensible, expanse. But black holes defy that simplicity. They are like tears in the fabric of space and time, regions where our familiar concepts, mass, energy, time, even causality, start to break down. Their immense gravitational forces warp space and stretch time, bending reality into configurations that challenge the framework of relativity. The physics that explains falling apples and orbiting planets grows unreliable in their shadow. Around these cosmic voids, matter behaves in strange and unpredictable ways. Energy spirals inward, light is trapped and twisted, and even the structure of space can contort. This leads to questions that edge into the philosophical. When material enters a black hole, does it cease to exist? Is it transformed into something new, something unrecognizable by our current science? Our models grow fuzzy at these extremes, requiring new theories that may one day supersede even Einstein's insights. As black holes consume nearby matter and grow in mass, they may even influence the life cycle of galaxies, altering how stars form and how structures evolve. These cosmic engines don't merely exist, they shape the universe around them and push the boundaries of our understanding outward. In parallel, another revelation has transformed our view of the universe: the discovery of exoplanets. For much of human history, our solar system seemed to define the extent of planetary possibility. Our attention was fixed on the familiar orbiting bodies, planets, moons, asteroids, circling our own sun. But when astronomers began detecting planets orbiting distant stars, that narrow view shattered. It was as though we had believed our small pond to be the whole ocean, only to discover an endless sea teeming with wonders. Each new exoplanet confirmed expands the cosmos not just in distance but in diversity. Some are enormous gas giants that dwarf Jupiter, while others are rocky, Earth-like spheres orbiting within the so-called habitable zone of their stars. These discoveries provoke thrilling questions. What does it truly take for life to arise? Could there be other planets with liquid water, with atmospheres, perhaps even with intelligent civilizations gazing skyward and wondering if they are alone? Together, black holes and exoplanets embody two extremes of cosmic inquiry. One probes the void, where known laws dissolve, while the other opens doors to new worlds, where life might be just beginning. Each deepens the mystery of existence. Each forces us to rethink what we thought we knew. In the grand documentary of the universe, they are chapters still unfolding, narratives that challenge, inspire, and beckon us onward into the unknown. Moreover, the techniques employed to detect exoplanets have revolutionized the way we explore the universe. One of the most groundbreaking methods involves observing the subtle dimming of a star's light as a planet crosses in front of it, a phenomenon known as a transit. This approach has unlocked entirely new avenues of investigation, allowing astronomers to probe far beyond our solar system. With this technique, scientists can now study the atmospheres of these distant worlds, searching for chemical markers that might signal the presence of water or even signs of life itself. This quest has transformed the field into a vibrant, multidisciplinary endeavor. No longer confined to simply cataloging stars and planets, researchers now focus on the profound implications these discoveries hold. The implications ripple across scientific disciplines, prompting astrophysicists, planetary scientists, and biologists to collaborate in unprecedented ways. Together, they strive to understand not only how these planets form, but also how they might change over time and what they could mean for humanity's future. The search for exoplanets has dramatically shifted our perspective. Instead of a narrow focus on our own solar system, we now see a universe teeming with diversity and dynamism, filled with possibilities waiting to be explored. This excitement fuels a broader curiosity, driving fundamental questions about our place in the cosmos. The universe ceases to be a mere backdrop to human existence. It becomes a boundless playground of discovery, holding secrets about life and what lies beyond. Central to this exploration is the Hubble Space Telescope, which plays a vital role in expanding our cosmic understanding. Orbiting high above Earth's atmosphere, Hubble enjoys an unobstructed view of space, free from the blurring effects caused by the air. Its powerful lenses capture breathtaking images and gather data that reveal the complex details of distant galaxies, stars, and other celestial phenomena. One of Hubble's most remarkable capabilities is its ability to peer deep into space and back in time. By observing light that has traveled for billions of years, Hubble allows scientists to witness the birth and evolution of galaxies as they existed shortly after the Big Bang. This glimpse into the early universe helps researchers determine its age and measure its expansion, shedding light on fundamental questions about how it began and where it might be headed. Hubble's impact extends to the study of exoplanets as well. By analyzing starlight filtered through the atmospheres of these far-off worlds, it helps detect chemical signatures that could indicate habitability or even life. The telescope also contributes to our understanding of black holes, observing how these mysterious objects influence nearby stars and gas. Through ongoing cooperation with other observatories and instruments, Hubble continues to refine cosmological models, turning each new discovery into a stepping stone for further exploration. In this way, Hubble acts as a bridge between what we know and the unknown, illuminating the edges of the universe and inspiring us to push beyond them. Within the realm of theoretical physics, cosmic censorship theory addresses the puzzling nature of black holes and the limits of our cosmic knowledge. The theory suggests that certain extreme cosmic events, especially those involving black holes, should never produce observable contradictions or naked singularities that defy the laws of physics. To visualize this, imagine gazing at the surface of a perfectly still lake. Everything looks calm and orderly. Now, picture throwing a stone into the water, causing ripples that disturb the surface. Similarly, black holes create enormous distortions in the fabric of space and time, but cosmic censorship proposes that these distortions are always hidden behind an event horizon, a boundary beyond which no information can escape. This means that while the singularity inside a black hole, where gravity becomes infinitely strong, is a region of extreme chaos, it remains concealed from our view. The event horizon acts as a cosmic curtain, shielding us from the bewildering physics occurring within. This concept has profound consequences for our understanding of the universe's boundaries. It implies that there could be realms disconnected from the reality we can observe, reinforcing the idea that despite our technological advances, some mysteries will always lie beyond our reach. Cosmic censorship not only informs how we think about black holes, but also highlights the inherent limits of human knowledge concerning the cosmos. It reminds us that while we can study galaxies, stars, and other celestial bodies in great detail, the most extreme phenomena might forever remain hidden, wrapped in the very fabric of space and time. Even as modern space telescopes make astonishing discoveries, they face inherent observational challenges. One significant limitation is their field of view. Many telescopes are designed to fall into focus on small, specific regions of space, which means they might miss larger or more distant phenomena occurring beyond their sight. To build a comprehensive picture of the universe, astronomers often have to combine multiple observations taken over time, stitching together these snapshots, like pieces of an enormous cosmic puzzle. Another challenge lies in the sensitivity of these instruments. Telescopes rely on capturing faint light from distant objects, but their effectiveness can be compromised by interference from cosmic dust, or the background glow of nearby stars and galaxies. This background noise can easily drown out the subtle signals coming from far-flung celestial bodies, making it difficult to observe and analyze them accurately. Despite these hurdles, the pursuit of knowledge continues relentlessly, propelled by human curiosity and the desire to unravel the universe's deepest secrets. Each advancement in telescope technology brings us closer to understanding not only the vast cosmos, but also our own place within it. Moreover, the range of wavelengths that telescopes can detect defines their observational capabilities. Most space telescopes are designed to focus on specific portions of the electromagnetic spectrum, such as visible light or infrared. This specialization means they might miss valuable information present in other wavelengths, like X-rays or radio waves. To truly understand the universe in all its complexity, scientists must combine data from these various forms of light. Another important factor affecting observations is the telescope's orbit and position. Although being above Earth's atmosphere reduces interference caused by atmospheric effects, telescopes in low Earth orbit can still be vulnerable to light pollution from cities if not properly shielded. Additionally, telescopes in orbits that are not perfectly stable can face disruptions that hinder their ability to continuously track celestial objects over time. Technological limitations also pose challenges. Issues like limited resolution and the impact of cosmic rays can interfere with the accuracy of data collection and analysis. Cosmic rays are high-energy particles traveling through space from all directions, and their interaction with telescope instruments can add unwanted noise to the observations. Furthermore, processing the enormous amounts of data produced by these telescopes is itself a complex task, requiring innovative computational techniques and resources to extract meaningful scientific insights. While space telescopes are incredibly powerful tools for exploring the cosmos, factors such as their limited fields of view, sensitivity to certain wavelengths, orbital challenges, and technological constraints all contribute to the complexity of space observation. Each element shapes what scientists can learn about the universe and highlights the ongoing need for advancements in telescope design and technology. Cosmic rays deserve special attention. These particles, originating from sources like supernova explosions and the energetic centers of distant galaxies, known as active galactic nuclei, act as messengers from the farthest reaches of space. As they journey through the universe, cosmic rays interact with magnetic fields and other particles, changing their direction and energy. This process acts like a cosmic GPS system. By studying the arrival patterns of cosmic rays on Earth, scientists can deduce information about their origins and the environments they traveled through. The energy distribution and composition of cosmic rays reveal crucial details about space conditions, including magnetic fields and the density of intergalactic matter. They point to energetic regions in space, hinting at boundaries and large-scale structures such as galaxy clusters. Moreover, cosmic rays provide indirect ways to study dark matter, the mysterious substance thought to make up most of the universe's mass. By analyzing how dark matter might influence cosmic ray behavior, researchers gain valuable clues about the universe's composition and the forces at its edges. Turning to cosmic background noise, it presents a major challenge for scientists observing the universe. This noise can be imagined as a static-filled clutter or whispers blending into the vast cosmic symphony. It primarily stems from the cosmic microwave background radiation, a relic from the Big Bang that fills space uniformly. Although this ancient radiation is essential for understanding the early universe, it can overwhelm faint signals from distant galaxies or elusive phenomena like dark matter. Separating meaningful signals from this pervasive noise is like trying to listen to a soft conversation amid a roaring crowd. Observational instruments, including telescopes themselves, can introduce additional noise, similar to an old radio producing crackling sounds. These unwanted signals, whether electronic interference or ground-based sources, mix with cosmic noise, complicating data analysis. To overcome these obstacles, scientists use advanced signal processing techniques to filter out noise and extract useful information. This requires not only sophisticated algorithms, but also a deep understanding of the nature of both the desired signals and the noise. Navigating through this cosmic cacophony is essential for uncovering the universe's secrets and learning about its formation and evolution. Gravitational waves add another fascinating dimension to cosmic observation. These ripples in the fabric of space and time are produced by some of the universe's most violent events, like the collision of black holes or neutron stars. Imagine dropping a stone into a pond and watching the ripples spread outward. Gravitational waves behave in a similar way, traveling through space and carrying crucial information about their origins. Unlike light, gravitational waves can pass through matter almost unaffected, allowing scientists to peer into phenomena hidden behind stars or entire galaxies. This unique ability offers a new window into the universe, revealing events that would be otherwise invisible. By detecting and analyzing these waves, researchers can learn about the properties of the massive objects that created them, such as their masses, spins, and distances. Studying gravitational wave patterns helps astronomers understand the behavior of the universe itself. For example, waves produced by merging black holes provide insights into how these enigmatic objects form and evolve, challenging existing theories about their development. Through these cosmic vibrations, humanity gains a deeper understanding of the forces shaping the cosmos. Furthermore, gravitational waves unlock remarkable insights into the universe's expansion by revealing details about its speed and history. This groundbreaking method of cosmic exploration opens the door to studying phenomena that remain largely mysterious, such as the intricate processes inside neutron stars or the enigmatic nature of dark matter. These waves act as messengers from the cosmos, delivering information about the universe's structure in ways that traditional light-based observations cannot. By enriching our understanding of the cosmos, gravitational waves help answer fundamental questions about the very fabric of reality. Gamma-ray bursts rank among the most powerful explosions in the universe, often seen as cosmic beacons guiding scientists deeper into space exploration. These bursts release an enormous amount of energy across a broad range of wavelengths, with gamma rays leading the charge. Imagine them as brilliant flashes of light occurring when massive stars collapse catastrophically into supernovae, or when two dense neutron stars collide, unleashing bursts of energy so intense they temporarily outshine entire galaxies. Their incredible brightness allows astronomers to observe them across vast cosmic distances, sometimes billions of light years away, giving a glimpse into the universe's distant past. Because these bursts happen in regions far from our own galaxy, they serve as cosmic lighthouses illuminating the remote universe and shedding light on the conditions of its earliest epochs. Studying gamma-ray bursts offers profound implications for understanding cosmic structures and processes. By analyzing the light emitted during these events, scientists can gather information about the interstellar medium where the bursts originate. This, in turn, reveals details about star formation, the life cycles of stars, and the evolution of galaxies on a grand scale. In a broader sense, gamma-ray bursts push the boundaries of fundamental physics by challenging our knowledge of gravity, matter, and energy. They inspire advances in technology as researchers develop sophisticated instruments and methods to detect and interpret these distant signals. As our tools grow more precise, our horizons expand, unveiling new cosmic mysteries and deepening our understanding of universal phenomena. The dazzling light show from gamma-ray bursts is not merely a spectacle. It actively fuels humanity's quest for knowledge about the universe we call home. The Oort cloud can be imagined as an immense spherical shell surrounding our solar system, marking the outer boundary of our current cosmic neighborhood. Picture a vast swarm of icy bodies lingering far beyond the farthest known planets, like an invisible fence defining the edge of our solar system. This distant region, believed to be packed with comets and frozen remnants from the solar system's formation, shapes how scientists think about what lies beyond our immediate celestial surroundings. Though the Oort cloud itself has never been directly observed, its existence is inferred from the behavior of long-period comets that seem to come from this far-off domain. Occasionally, these comets travel inward toward the Sun, offering glimpses into the material that may be stored in this remote zone. More than just a boundary, the Oort cloud challenges our perception of the universe's limits. It suggests that the solar system is not an isolated entity, but part of a far larger, more complex cosmic environment. This distant realm raises fascinating questions about what else might lie hidden beyond our sight in the vastness of space. It represents the frontier of the solar system's influence and hints at the existence of mysterious phenomena, including distant star systems and celestial bodies yet to be discovered. Rather than viewing the universe as a finite space, the Oort cloud encourages a perspective filled with endless possibility, inspiring both scientists and dreamers to contemplate the unknown expanses that lie just beyond our reach. Quantum mechanics plays a crucial role in shaping our understanding of the universe, especially when exploring its most extreme and puzzling aspects. At the tiniest scales of reality, particles do not behave like solid, predictable objects. Instead, they exhibit wave-like properties that blur the boundaries of classical behavior. This fundamental principle gives rise to phenomena that often appear strange and counterintuitive, transforming our comprehension of everything from the fabric of space-time to the very essence of energy. In realms like black holes and the Big Bang, quantum mechanics introduces ideas such as uncertainty and superposition that challenge traditional deterministic views. For example, within a black hole, gravity compresses matter to unimaginable densities, creating an environment where quantum effects become impossible to ignore. Near the event horizon, the boundary beyond which nothing can escape, quantum fluctuations cause particles to momentarily pop in and out of existence. These strange phenomena may even hint at the creation of new universes or relate to the information paradox, a profound mystery about what happens to information consumed by black holes. Moreover, when we delve into the earliest moments of the universe, right at the moment of the Big Bang, quantum mechanics becomes a crucial lens through which we can understand how particles behaved under unimaginably intense energies and densities. These quantum fluctuations, tiny random variations in energy, might have sown the very seeds that grew into the vast structures we see today: galaxies, clusters, and cosmic webs. Picture these fluctuations as faint ripples on the fabric of space-time, the earliest echoes in a universe that was still forming. These small irregularities in energy density could have been the catalysts for everything from stars to planets, essentially laying down the blueprint for the cosmos as we know it. The interaction between quantum mechanics and cosmic phenomena reveals a world full of strange but essential concepts that challenge our common sense and reshape our understanding of the extremes of space and time. To truly grasp the workings of the universe, we must embrace the strange and counterintuitive world of quantum physics, where the usual rules break down and reveal a more intricate, deeply connected reality. One of the most intriguing ideas emerging from this exploration is string theory. This theory stretches beyond the traditional notion of the universe being made up of simple point-like particles. Instead, it proposes that these particles are tiny vibrating strings, more like miniature rubber bands oscillating at various frequencies. The way these strings vibrate determines the particle's fundamental properties, its mass, charge, and more. This perspective opens a whole new way of thinking about the universe, especially at its edges. While we often imagine the universe as a vast, three-dimensional space, string theory suggests there could be many more dimensions hidden from our senses, potentially up to 10 in total. These extra dimensions might influence how the edges of our universe behave. Instead of being a clear-cut boundary or a dead end, the edge might act more like a portal or gateway to these unseen realms. This challenges the idea of the universe having a simple end, and suggests that beyond what we can observe, reality could be intertwined with higher dimensions, fundamentally shaping how we experience existence. Furthermore, string theory pushes us to view the universe as part of a larger, interconnected, multidimensional structure. Far from being isolated, our cosmos could be a single thread in a vast and complex tapestry that stretches across dimensions we cannot yet perceive. This shifts how we think about the universe's boundaries, blending what we know with what remains unknown, and hinting at an endless expanse of possibilities beyond our current understanding. In this light, traditional views of the universe's edge as a final boundary give way to a more fluid and interconnected vision, where borders dissolve and the cosmos is woven into a vibrant, multidimensional fabric still waiting to be fully explored. Another mind-bending idea that emerges in this context is the holographic principle. This theory proposes that all the information contained within any volume of space could be fully represented on a two-dimensional surface, much like a hologram projects a three-dimensional image from a flat plane. Imagine our entire universe with all its depth and complexity encoded on a surface, such as the boundary of a black hole. This concept fundamentally challenges our usual understanding of space and dimensions. It suggests that the familiar laws of physics governing our three-dimensional world might arise from processes happening on this two-dimensional boundary. If we consider the universe as having limits, the holographic principle offers a remarkable way to explain how the immense amount of information in the universe could fit into what seems like a much smaller amount of data. The detailed complexity of our three-dimensional reality may not be rooted in space itself, but could emerge from a more basic layer of existence that stretches beyond our perception. In essence, both string theory and the holographic principle invite us to rethink the universe on the grandest scales. They push us to move past old ideas of clear-cut edges and finite boundaries, instead presenting a cosmos where dimensions merge, realities overlap, and the vastness we observe is just one layer of a far richer and more mysterious whole. This new understanding encourages a sense of wonder and curiosity about what lies beyond the limits of what we can see and measure, revealing the universe as a far more intricate and interconnected masterpiece than we ever imagined. Furthermore, this principle delves into profound questions about what exists at the very edges of the universe. If space itself can be understood as information encoded on a surface, this notion hints that our observable universe may be confined or bounded in some way. Such a boundary might help explain puzzling phenomena like the cosmic horizon, the ultimate limit beyond which we cannot see. This idea opens up deep implications for our understanding of gravity, black holes, and the very fabric of space and time. As we explore these cosmic boundaries, the holographic principle provides a tantalizing glimpse into the possible limits of the universe. It invites us to reconsider how we perceive reality at its most fundamental level, challenging the traditional views that space and time stretch infinitely without boundary. Alongside this, the simulation hypothesis proposes that what we experience as reality might not be the original one. Instead, it might be a highly advanced simulation crafted by an intelligent civilization far beyond our own. This provocative idea leads to intense discussions about the nature of consciousness, existence, and the universe itself. When combined with universal edge theories, those that suggest there are limits or boundaries to our universe and even the laws of physics, our perspective widens dramatically. Imagine standing at the shore of a vast cosmic ocean. The shoreline represents the edges of what we currently understand, the limits of our knowledge. Beyond that shore lies the unknown. The simulation hypothesis encourages us to consider that our entire universe, with all its rules and apparent boundaries, might be just a small part of a much grander reality, governed by beings capable of controlling or manipulating these very limits. If the universe is a simulation, then these edges might not be ultimate constraints. Instead, they could be the programmed rules within this artificial environment. The laws of physics might resemble the rules of a game, defining how players interact within a specific context. However, these rules could be altered or rewritten if the creators of the simulation so desired. This idea raises thrilling questions about what might lie beyond our current limited perspective. Moreover, some interpretations of the simulation hypothesis suggest that, just as computer simulations can vary enormously in complexity and structure, the universe itself might consist of multiple layers. Each layer could be a different simulation or reality intertwined with others. Universal edge theories then serve as tools to speculate about what might exist beyond the simulation we perceive, opening the door to concepts such as parallel worlds, alternate dimensions, or other forms of existence still beyond human comprehension. By merging the simulation hypothesis with universal edge theories, we are compelled to rethink our fundamental assumptions about reality. We must consider our place within it and the possibility of realms far beyond the scope of everyday experience. It challenges us to ask whether what we perceive is nothing more than data flowing through a vast program designed for purposes we have yet to understand, be it exploration, learning, or something else entirely. Another captivating concept, the anthropic principle, offers insight into why the universe appears so finely tuned for life. At its core, this principle suggests that the fundamental properties of the universe are precisely calibrated to allow conscious beings to emerge, beings who can observe and contemplate the cosmos itself. Picture the universe as a grand stage where specific conditions must be met for life to flourish. If the fundamental forces or constants of nature were even slightly different, life as we know it might never have arisen. This shifts our view of the universe from a place governed solely by natural laws to one where observers themselves play a significant role. The anthropic principle can be understood in two ways. The weak version simply states that the universe must allow for life because we are here to observe it. The strong version goes further, suggesting the universe exists in the way it does precisely because it must support conscious observers. Exploring the anthropic principle leads us to profound implications for cosmology and the idea of fine-tuning. Some scientists propose that an infinite number of universes might exist, each with different laws and physical constants. Within this multiverse theory, it is not surprising that we find ourselves in a universe capable of supporting life, simply because we could not exist in any other. This principle pushes us to examine the boundaries between science and philosophy, urging us to reflect on our place within the grand tapestry of reality. Ultimately, the anthropic principle broadens our perspective. It suggests the universe is not a cold, indifferent expanse, but possibly a domain where consciousness has a vital role. Turning to speculative technologies, ideas like warp drive spark fascinating discussions about the boundaries of our universe. The concept of a warp drive, rooted in theoretical physics, proposes a way to travel faster than light by manipulating space itself. Imagine a bubble of warped space surrounding a spacecraft, contracting space in front of it while expanding space behind, enabling travel across vast cosmic distances in a fraction of the time it would normally take. This concept challenges the conventional understanding of speed limits imposed by the laws of physics and has implications far beyond mere travel. If a warp drive were possible, it could revolutionize our understanding of the universe's structure and limits. While scientists currently believe the universe is finite and continuously expanding, with galaxies moving away from one another, warp drives suggest that intergalactic travel might become feasible, making previously unreachable parts of the cosmos accessible. Such technology would demand a radical reevaluation of what defines the edges of the universe and might reshape our understanding of cosmic boundaries forever. Moreover, warp drives open the door to exploration into realms far beyond the limits of known physics. These theoretical machines could enable humanity to traverse vast regions of space that currently seem unreachable using conventional travel methods. Such a breakthrough would not just speed up travel, but force a fundamental rethinking of cosmic geography. This shift could revolutionize our study of celestial phenomena, granting us access to areas of the cosmos that were once completely off limits. Yet, despite their tantalizing promise, warp drives remain speculative, like raising profound questions about causality, the fabric of space-time, and the very essence of reality. Should such technology become a reality, it would not only redefine how we navigate the universe, but might also challenge the core principles that govern physics, demanding a deeper inquiry into the fundamental structure of existence. Tachyons, hypothetical particles, further stretch the boundaries of our understanding. These elusive particles, if they exist, would constantly travel faster than light, defying our current concepts of speed and motion. Unlike ordinary particles, which gain mass as they near the speed of light, tachyons would behave in the opposite manner. Their mass would decrease as they accelerate, allowing them to surpass light speed. The existence of tachyons could unlock insights into realms beyond our universe, often imagined as the multiverse. If tachyons can cross these dimensions faster than light, they might carry signals or information almost instantaneously across vast cosmic distances, bridging gaps impossible for normal particles. This ability provokes fascinating questions about spacetime's architecture itself. Detecting tachyons or their effects could reveal clues about the fundamental nature of reality, hinting at alternate universes, or offering glimpses into the earliest moments after the Big Bang, before light could freely travel. While still speculative, tachyons open theoretical pathways that could expand our grasp of what lies beyond the observable cosmos and transform our perspective on existence itself. Time dilation and relativity are central to understanding the universe's vastness and the limits of what we perceive. At the heart of Einstein's theory of relativity lies the concept that time is not fixed. Instead, it fluctuates based on an object's speed and position relative to gravitational fields. Picture a spacecraft hurtling through space at a speed close to light. For the astronauts inside, time would flow normally, but for observers back on Earth, years could pass in what seems like moments. This phenomenon, known as time dilation, shows that the faster you travel, the slower time moves for you compared to someone who remains stationary. This concept challenges our basic understanding of the universe and opens the door to intriguing possibilities. Because light from distant galaxies has traveled billions of years to reach us, if humanity one day achieves near-light speed travel, explorers might experience relatively brief journeys while witnessing cosmic history unfolding over vast spans of time for those on Earth. Additionally, relativity suggests the universe's boundaries are not fixed but fluid, as the cosmos constantly expands and time behaves differently under varying conditions. This invites speculation about multiverses and dimensions beyond current comprehension. Time dilation becomes more than a scientific curiosity. It becomes a gateway to profound theories about the universe's true scope and what may lie beyond our limited perception, while beckoning us to explore not only space, but the very essence of existence. As we stand on the threshold of a new age of discovery, emerging technologies promise to deepen our understanding of the universe's edges. Imagine highly sophisticated telescopes equipped with advanced sensors capable of detecting light from the most distant parts of space, exploring cosmic regions that were once beyond our reach. These instruments will not just extend our vision, but will also collect data across a spectrum of light, uncovering secrets hidden from our current observational capabilities. With the rise of powerful computers and artificial intelligence, analyzing this vast influx of information will transcend traditional methods. AI could identify patterns and anomalies in cosmic background radiation or other phenomena, unveiling clues about the universe's structure, its expansion, and possibly its ultimate destiny. This evolution will transform cosmology, refining models of galaxy formation, collision, and interaction over billions of years. In parallel, advancements in space travel technology could enable probes to venture into unexplored regions of the universe, delivering first-hand data and experiences from environments never before encountered. Imagine a probe journeying between galaxies, measuring the intergalactic medium, dark matter, and the effects of cosmic radiation on the universe's architecture. Additionally, gravitational wave detectors might reveal unseen aspects of the cosmos, detecting ripples in space-time caused by massive events such as black hole mergers or neutron star collisions. As these instruments become increasingly sensitive, they will deepen our understanding of the universe's dynamics and boundaries. Together, these emerging technologies will not only expand our knowledge, but also challenge existing frameworks and theories about the universe. Our understanding of its limits could shift dramatically as we unlock new dimensions of information, inspiring renewed curiosity and insight. The universe is filled with profound mysteries, particularly regarding its boundaries. One of the most compelling questions concerns its expansion. Much like a balloon inflating and stretching, the universe itself is expanding, pushing galaxies away from each other, reshaping the cosmic landscape in ways that continue to surprise and inspire. However, observations reveal that the expansion of the universe is not just continuing, it is accelerating. This discovery poses a profound mystery. What is the force behind this acceleration? Scientists often call it dark energy, a term that hints at something unknown and powerful. Despite making up a vast portion of the universe's total composition, dark energy remains one of the greatest enigmas in modern astrophysics. Its true nature is hidden from us, and understanding it could reshape our grasp of the cosmos itself. Another equally fascinating puzzle centers on the idea of the observable universe. The universe stretches far beyond what our eyes and instruments can detect. Because light travels at a finite speed, we only see objects whose light has had enough time to reach us since the universe began. This limitation forms a cosmic horizon, an invisible boundary that defines the edge of our knowledge. Beyond this horizon lies an expanse we cannot directly observe. Some scientists speculate that this hidden realm may contain structures or phenomena that defy our current laws of physics, waiting quietly beyond our reach. Dark matter adds yet another layer to this cosmic mystery. It is a form of matter that neither emits nor absorbs light, making it completely invisible to traditional telescopes. However, its existence is inferred through the gravitational effects it exerts on galaxies and other visible matter. This unseen substance shapes the cosmic web, influencing the formation and motion of galaxies across vast distances. Dark matter constitutes a significant fraction of the universe's mass, yet its precise identity remains unknown, cloaked in secrecy and continuing to challenge our understanding. Adding to these questions is the possibility that our universe may not be the only one. The multiverse theory suggests that there could be numerous universes, each governed by its own distinct physical laws and constants. If this is true, it would revolutionize how we think about reality, placing our universe within a far grander cosmic context. These ideas push the boundaries of science and philosophy, hinting at a universe, or rather a multiverse, far more complex and layered than previously imagined. These cosmic mysteries expose the limits of human knowledge and inspire a relentless pursuit of discovery. Each new exploration brings us closer to understanding the universe, even as it reveals how much remains unknown. Unexplained phenomena have long been the driving force behind scientific breakthroughs, urging researchers to expand the horizons of what we know. Imagine standing on the shore of a vast ocean, staring out toward an endless horizon. Just as ancient sailors were compelled to venture beyond the visible sea, scientists today are motivated to explore the mysteries of the cosmos. Phenomena such as dark matter, dark energy, and gravitational waves challenge the frameworks that have guided our thinking for decades. They force us to reconsider fundamental assumptions about the universe. Dark matter, for instance, was proposed after astronomers observed that galaxies rotate at speeds that should cause them to tear themselves apart if only visible matter were present. The idea of an invisible mass holding galaxies together reshaped our understanding of cosmic structure. Yet, despite decades of study, the true nature of dark matter remains a secret. Similarly, dark energy's role in accelerating the universe's expansion challenges the traditional view that gravity is the dominant cosmic force, one that should slow this expansion over time. Instead, dark energy appears to act in opposition, pushing galaxies apart with increasing speed. This forces a rethinking of the very fabric of space and our place within it. Gravitational waves add another dimension to this unfolding story. These tiny ripples in spacetime, detected only recently, provide new ways to observe cosmic events such as black hole mergers and neutron star collisions. They reveal a universe that is far from static, constantly changing, and filled with dramatic interactions. Each of these phenomena pushes scientists to revise or create new models, demonstrating the dynamic and evolving nature of scientific inquiry. Humanity's curiosity drives us to unravel these mysteries, expanding our understanding of the cosmos across both time and space. Astronomical anomalies, unexplained behaviors, or observations that don't fit existing theories are especially valuable in this pursuit. When stars behave unexpectedly, or galaxies show unusual patterns of mass distribution, scientists are forced to confront the gaps in their knowledge. These anomalies often become the seeds of innovation, encouraging researchers to develop new ideas or refine existing ones. Take dark matter once again. It emerged as a concept when observations showed galaxies spinning too fast to be held together by visible matter alone. The invisible mass needed to explain this led to the hypothesis of dark matter. Yet, many anomalies related to dark matter suggest the universe might operate under physical principles we have yet to fully grasp. Likewise, the rapid acceleration of the universe's expansion stands as a glaring anomaly. Traditional physics would predict a slowing expansion due to gravity's pull, but observations show the opposite. This surprising discovery propelled the dark energy hypothesis, underscoring the presence of unknown forces influencing the cosmos. These anomalies do more than challenge current theories. They drive scientific progress. They inspire explorations into quantum physics, alternative gravity models, and even extra dimensions of space, opening new avenues for understanding the universe's deepest secrets. At the very edges of knowledge, where the universe displays its most perplexing phenomena, scientists engage in a careful process of investigation. When data contradicts expectations, they scrutinize the observations, ensuring measurements are precise and free of error. Advanced technologies like cutting-edge telescopes and powerful computer simulations assist in refining this information. Once confidence in the data is secured, researchers revisit theoretical frameworks. Sometimes adjustments to existing theories resolve the contradictions. Other times, the discrepancies demand revolutionary ideas that fundamentally alter our understanding. This iterative process exemplifies how science advances, not through certainty, but through questioning and revision. For example, the discovery of the universe's accelerating expansion forced cosmologists to introduce the concept of dark energy, a powerful but mysterious force reshaping the story of cosmic evolution. In this ongoing quest, the universe remains an ever-expanding puzzle, full of surprises and wonders. Every mystery invites us to push further, to learn more, and to deepen our appreciation of the vast cosmos that surrounds us. Ultimately, scientists engage in a continuous dialogue, sharing discoveries and fostering collaboration across the global research community. This collective effort sparks creativity and innovation, empowering researchers to explore alternative explanations and combine insights from a variety of scientific disciplines. In this way, contradictions between theory and observation, especially at the universe's outermost edges, do more than deepen our understanding. They propel the pursuit of knowledge further into the vast cosmic unknown. Deep space phenomena serve as gateways to unraveling the universe's complexities. Observations of distant galaxies reveal a vast cosmic tapestry woven with threads of events that stretch back to the universe's infancy. By studying the faint light emitted from these ancient galaxies, scientists gain vital insights into their formation and evolution, uncovering the intricate processes that have shaped them over billions of years. One of the most compelling mysteries illuminated by deep space observations is the existence of dark matter. Though invisible to direct observation, its presence is inferred through its gravitational effects on visible matter. This has led researchers to speculate about the true nature of this unseen substance, which appears to make up a substantial portion of the universe, fundamentally transforming our understanding of gravity and the formation of cosmic structures. In a similar vein, the discovery of cosmic microwave background radiation, a faint relic from the early universe, has offered researchers a glimpse into the conditions that existed mere moments after the Big Bang. This subtle glow provides critical evidence supporting the Big Bang theory, revealing that the universe began in a hot, dense state and expanded over time, cooling and evolving into the cosmos we observe today. The explosive deaths of massive stars known as supernovae also play a crucial role in expanding our cosmic knowledge. These spectacular events not only create and distribute heavy elements throughout the universe, but serve as standard candles for measuring cosmic distances. This allows scientists to map the universe's expansion and investigate the mysterious acceleration that seems to be driving it. More recently, observations of gravitational waves generated by colliding black holes and neutron stars have opened an entirely new chapter in our understanding of the cosmos. These waves confirm key predictions of Einstein's theory of general relativity and offer a novel way to gather information about cosmic events previously undetectable by traditional methods. Through the study of these deep space phenomena, scientists continue to peel back the layers of the universe's mysteries. From the enigmatic nature of dark matter and dark energy to the birth and growth of cosmic structures, every observation adds a new piece to the ever-expanding puzzle. This fuels humanity's relentless quest to comprehend our existence within this vast, largely unexplored cosmos. Quasars, short for quasi-stellar objects, rank among the brightest and most energetic entities in the universe. They act as remarkable cosmic beacons, illuminating our understanding of extreme conditions and events in the cosmos. At their core, quasars are powered by supermassive black holes located at the centers of distant galaxies. As gas and dust spiral into these monstrous black holes, they are heated to incredible temperatures, producing vast amounts of energy that can outshine entire galaxies. One of the most profound contributions quasars make to science is their role in probing the early universe. Many quasars we observe today emitted their light billions of years ago, allowing astronomers to glimpse how galaxies evolved shortly after the Big Bang. By studying this ancient light, researchers can uncover details about the universe's composition at that time, including how matter was distributed and how the first galaxies and stars formed. Furthermore, quasars are instrumental in testing the fundamental laws of physics under extreme conditions. The immense gravitational and energetic forces surrounding a quasar can generate phenomena not easily observed elsewhere. These extreme environments provide insight into the behavior of matter and radiation when gravity is extraordinarily strong, testing the limits of general relativity and known physics. Quasars also serve as crucial tools for measuring the expansion of the universe. By analyzing their light across vast distances, scientists calculate how quickly the universe is expanding and how this rate has changed over cosmic time. This research sheds light on dark energy, the mysterious force believed to be accelerating the universe's expansion. By observing and studying quasars, we not only marvel at some of the most extreme environments in the cosmos, but also gather vital clues about the universe's origins, evolution, and the fundamental forces that govern it. These fascinating objects illuminate pathways to knowledge, pushing the boundaries of what we understand about space and time itself. The discovery of nothingness at the edges of the universe would carry profound implications for our understanding of existence and the cosmos. In this context, nothingness refers to the absence of matter, light, and even the forces that usually shape our cosmic environment. This concept challenges our most fundamental beliefs about how the universe operates and what it means to be part of it. If regions of nothingness truly exist, it could imply that our universe is not a solitary entity, but rather one among many in a vast multiverse, a collection of universes, each with different properties and behaviors. This raises tantalizing questions about whether these other universes are accessible or remain forever unreachable, hidden in the immense void that separates them. Encountering nothingness might also reshape our understanding of the cosmos's evolution. It could suggest that the universe we observe is merely one phase in a larger cycle of expansion and contraction, a single chapter in an ongoing cosmic narrative. Such a realization would challenge current cosmological models, which depict the universe as an ever-expanding entity originating from a singular beginning. Through relentless observation and inquiry, scientists continue to explore these profound mysteries, pushing the boundaries of knowledge and transforming our understanding of the universe we call home. Moreover, when we begin to consider the concept of nothingness, it challenges us to rethink the very foundation of reality itself. The traditional ideas of space and time, which have long served as the framework through which we understand the universe, might break down or become irrelevant at these extreme edges of existence. This could suggest that what we perceive as the boundaries of the universe are far more fluid and dynamic than we have imagined. Such a revelation would open up profound existential questions about the nature of space itself. If parts of the universe truly embody absolute nothingness, it forces us to confront deep philosophical questions about existence and consciousness. Is life and awareness valuable because it stands in contrast to a vast void of nothing? The presence of nothingness could challenge our assumptions about why existence matters, pushing us to explore the meaning of life from a perspective that blends scientific discovery with philosophical introspection. Discovering nothingness, at the edges of the universe might rewrite everything we think we know about reality. It could unlock entirely new fields of inquiry and understanding, revealing dimensions of the cosmos previously hidden from view. Turning to another cosmic marvel, faint galaxy clusters serve as remarkable cosmic signposts in our quest to comprehend the universe's history and structure. These clusters, which are groups of galaxies held together by gravity, often lie far beyond our own Milky Way, making them difficult to observe. Yet their faintness is not a limitation. Instead, it offers scientists a unique window into the mysteries of dark matter, dark energy, and the growth of cosmic structures over time. When astronomers study these distant clusters, they engage in what can be called cosmic archaeology. The light reaching us today left these clusters billions of years ago, offering a rare glimpse into the ancient universe. By analyzing the makeup and distribution of these clusters, researchers gain crucial information about the spread of matter throughout the cosmos. This data is vital in understanding dark matter, the invisible substance that, despite being unseen, constitutes a large portion of the universe's total mass. One particularly fascinating effect observed in these clusters is gravitational lensing. Imagine using a magnifying glass to focus light on a distant object. Gravitational lensing works on a similar principle, where the immense mass of a galaxy cluster bends light passing near it. This bending of light not only magnifies distant objects, allowing us to see farther than ever before, but also reveals details about the cluster's mass and gravitational pull. This distortion offers essential clues about the hidden distribution of dark matter across the universe. Faint galaxy clusters also hold keys to understanding the universe's expansion. Their characteristics provide insights into dark energy, the mysterious force believed to be driving the accelerating growth of the cosmos. By studying the distances between clusters and how they interact, scientists can reconstruct how dark energy has influenced the universe's evolution over billions of years. Though they might seem insignificant at first glance, faint galaxy clusters are intricately woven into the fabric of cosmic investigation. They guide us in exploring some of the most elusive and strange components that govern our universe, bridging the gap from the earliest moments of cosmic history to the ongoing expansion today. Their study keeps the quest for cosmic knowledge continually advancing and deepening. Another extraordinary cosmic phenomenon captivating astrophysicists is fast radio bursts, or FRBs. These are brief, powerful flashes of radio waves originating from extreme distances, potentially billions of light years away. Despite lasting only a few milliseconds, an individual burst releases more energy than the sun emits in nearly a century. What makes these bursts so fascinating is their mysterious origin. Each appears to come from the depths of space, yet we have detected only a small number of them so far. Scientists have proposed numerous theories to explain these signals, ranging from the collapse of massive stars to interactions involving neutron stars. Some even suggest magnetars, highly magnetic neutron stars, might be responsible for these enigmatic bursts. The frequency and scattering of FRBs provide scientists with important clues about the cosmic environment through which their signals travel. For example, as the radio waves journey through space, they experience dispersion, a spreading out caused by interaction with matter. This dispersion helps reveal the presence of matter that cannot be observed directly, assisting researchers in mapping the invisible cosmic structures that influence how light moves across vast distances. Through studying fast radio bursts, scientists gain insight into not only these fleeting phenomena, but also the vast unseen web of matter that permeates the universe, enriching our understanding of the cosmos on the grandest scales. Moreover, the ability to detect these bursts and precisely locate their origins opens up entirely new pathways for comprehending the universe's grand evolution. By examining their patterns and frequencies, researchers hope to unlock profound secrets about the early universe's conditions, the intricate process of galaxy formation, and the complex interactions of cosmic matter. The enigmatic phenomenon of fast bursts of signals invites scientists to delve deeper into the vibrant and dynamic dance of celestial bodies, fostering new discoveries that enrich our understanding of the cosmos. Cosmic voids are immense, nearly empty regions of space containing far fewer galaxies than their surrounding areas. These vast stretches, often spanning hundreds of millions of light years, can be envisioned as the universe's hollow spaces. Studying these voids provides critical insights not only into the universe's large-scale structure, but also into the boundaries of our cosmic neighborhood. The existence of these voids reveals a fundamental characteristic of the universe's composition. As galaxies cluster under the relentless pull of gravity, they form a web-like network where dense filaments surround these enormous empty spaces. This arrangement shows us that space is far from uniform. Instead, it is a complex tapestry where matter concentrates in certain regions, leaving vast voids in between. When discussing the boundaries of the universe, we often refer to the limits of the observable universe, how far we can see with our current instruments. Cosmic voids play a significant role in this context, hinting at how matter and energy spread across the cosmos. While our observations reach only so far, the voids may extend well beyond that observable edge into areas currently beyond our detection capabilities. These sparsely populated voids raise fascinating questions about the universe's topology, that is, the very shape and structure of space itself. Imagine the universe as a three-dimensional balloon being inflated. In this analogy, cosmic voids might represent those patches on the balloon's surface that are less stretched, less expanded than others. They challenge our understanding of what lies beyond the visible realm, prompting profound inquiries about the ultimate fate of the universe. Does it extend infinitely, or is it contained within some unknown, uncharted structure? Far from being mere empty space, cosmic voids embody the variety and complexity of the universe. They suggest that while we understand our observable universe to have clear boundaries, the true nature of the cosmos might reveal vastly different landscapes, still waiting to be explored. Cosmologists play a crucial role in unraveling these mysteries surrounding the universe's edge, the farthest regions accessible to observation, and the limits of human understanding. These scientists blend cutting-edge observational techniques with sophisticated theoretical frameworks to explore the vast cosmos. Using advanced telescopes and sensitive instruments, cosmologists capture faint light emitted by distant galaxies, piecing together detailed maps of the universe's structure. These observations reveal not only the arrangement of galaxies and galaxy clusters, but also the elusive distribution of dark matter. Beyond observation, cosmologists rely on the principles of general relativity and fundamental physics to build models explaining how the universe has evolved from its birth to the present day. They study phenomena like cosmic microwave background radiation, a relic of the universe's fiery beginning, to gain insight into the early conditions and the ongoing expansion of the cosmos. By analyzing the movement and clustering of galaxies, they infer the universe's overall geometry and curvature, providing clues about its shape and fate. Their quest to understand the universe's edge leads them to investigate cosmic inflation, a theory describing a period of rapid expansion that occurred just moments after the Big Bang. This exponential growth set the stage for the formation of the structures we observe today. Through careful examination of cosmic microwave background data and distant galaxies seen as they were billions of years ago, cosmologists test the validity of this theory. Additionally, cosmologists study dark energy, a mysterious force thought to drive the accelerated expansion of the universe. By measuring how galaxies are distributed and analyzing light from exploding stars called supernovae, they seek to understand how this expansion affects cosmic structures and what it might mean for the universe's ultimate destiny. Their relentless research not only deepens our knowledge of the universe's edges, but also sparks new questions about what may lie beyond the limits of our current observations. Through these efforts, cosmologists weave together a detailed narrative about the cosmos, bridging gaps in understanding and confronting mysteries that remain tantalizingly out of reach. Astrophysics and cosmology, while distinct branches of astronomy, are deeply connected in the pursuit of unraveling the universe's secrets. Astrophysics focuses on the physical properties and behaviors of celestial objects, from the birth and death of stars to the enigmatic nature of black holes. Cosmology, on the other hand, contemplates the universe as a whole, its origins, evolution, structure, and eventual fate. The intersection of these disciplines becomes especially clear when exploring the universe's boundaries. Astrophysics provides the essential tools to analyze phenomena that shape our cosmic landscape. For example, understanding how stars live and die is critical in cosmology, because these processes create and distribute the elements necessary for forming galaxies, planets, and ultimately the emergence of life itself. Conversely, cosmological theories provide a vast and sweeping framework within which astrophysics can dig deeper and uncover finer details. The Big Bang Theory, a foundational pillar of cosmology, suggests that the universe has been expanding ever since its origin. Astrophysicists take this idea and examine it through the lens of real observations, such as the red shift of distant galaxies. This red shift occurs when the light emitted from galaxies stretches toward longer wavelengths as they speed away from us, offering clear evidence of the universe's ongoing expansion. This phenomenon not only confirms that space itself is growing, but also helps define the boundaries between what we can observe and what remains beyond our reach. This sparks profound questions about how much of the universe lies hidden beyond what we can see or measure. Together, cosmology and astrophysics engage in a collaborative effort to tackle some of the most fundamental mysteries in science, including the elusive nature of dark matter and dark energy. These unseen forces play critical roles in shaping the universe's expansion and its large-scale structure. Observations of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, and measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, feed into cosmological models. This feedback loop sharpens our understanding of the universe's makeup and its evolutionary journey. While astrophysics dives into the study of individual cosmic objects and phenomena, cosmology paints the big picture, offering humanity a grand narrative to explore the edges of existence and contemplate what might lie beyond those edges. This joint endeavor enriches our comprehension of the cosmos and opens up fascinating discussions about the possibility of multiple universes, the true nature of space-time, and the ultimate fate of all that exists. The quest to understand the limits of the universe highlights the necessity of blending both astrophysical and cosmological viewpoints. Meanwhile, technological advances in physics continuously transform our grasp of the universe's boundaries, the ultimate frontiers that dictate how the cosmos behaves. Such technological progress has turned once purely theoretical concepts into areas ripe for investigation and experimentation. The invention and enhancement of powerful telescopes, for example, have revolutionized our ability to observe distant galaxies, stars, and cosmic events. These instruments capture light that has traveled for billions of years to reach Earth, providing invaluable insights into the early stages of the universe and revealing the expanding limits of space and time. Similarly, particle detectors housed deep underground enable scientists to observe rare particles produced by phenomena predicted by physics, such as potential interactions involving dark matter. These observations deepen our understanding of the universe's fundamental building blocks and push the boundaries of particle physics knowledge. Advancements in collider technology also allow researchers to smash particles together at incredible speeds, recreating conditions that existed just moments after the Big Bang. By doing so, scientists probe the fundamental forces and particles that govern reality, searching for points where current physics models may fail, whether due to energy limits or unexplained phenomena. On another front, breakthroughs in computational technology empower scientists to run complex simulations that model physical interactions too intricate or extreme to reproduce in a laboratory. These simulations test theories about black holes, the behavior of time and space, and the boundaries of physics under conditions beyond everyday experience. Every new technological development unlocks new pathways for questioning established theories and exploring realms once thought inaccessible. This continual cycle of discovery forces us to constantly reevaluate what we understand about the universe and its fundamental limits. Each breakthrough serves as a foundation for further exploration, guiding us toward deeper inquiries about the very nature of reality itself. Space missions add a crucial layer to this understanding by collecting massive amounts of data about celestial bodies, cosmic phenomena, and the environment of space. When spacecraft are launched, they gather detailed readings of temperature, light spectra, and even gravitational influences exerted by distant objects. Through painstaking analysis of this information, scientists extract meaningful insights. For example, studying the atmospheres of distant planets can provide potential to support life, shaping our search for habitable worlds beyond Earth. Additionally, data collected from telescopes observing light emitted by ancient stars provide crucial clues about how the universe formed and evolved over billions of years. Moreover, space missions frequently investigate fundamental questions that have long puzzled scientists, such as the origin of cosmic rays, the mysterious presence of dark matter and dark energy, and the complex behavior of black holes. By carefully analyzing these rich datasets, researchers can develop detailed models and simulations that predict how various celestial phenomena might behave under different conditions. This growing understanding has the potential to lead to major breakthroughs in both physics and astronomy, guiding future space explorations and expanding our knowledge of the fundamental forces that govern the cosmos. The collaborative nature of this work is essential. Scientists across the world share knowledge, as different space missions often focus on different aspects of the universe. When these diverse datasets are combined, they deepen our understanding and provide opportunities to confirm or challenge existing scientific theories. In this way, data analysis from space missions transcends simple observation. It becomes a powerful tool that transforms raw information into profound discoveries about the universe and our place within it. Computer simulations are especially valuable in this process. They serve as sophisticated tools that help scientists visualize and comprehend the vast, often abstract regions of the universe. Think of these simulations as intricate virtual models that mimic real-world physical processes on a smaller, manageable scale. By creating complex algorithms that replicate the fundamental laws of physics, researchers can explore phenomena that would otherwise be impossible or incredibly difficult to observe directly in space. Conditions in outer space can vary dramatically, from the dense formations of stars to the elusive patterns of dark matter, which is believed to exist in vast amounts but cannot be observed directly. Simulations allow scientists to create virtual environments where they can experiment with different variables and scenarios. For example, they might adjust the mass of celestial bodies or change the rates of expansion in various regions of space to study how these factors affect gravitational interactions and the overall structure of the universe. These simulations also help illustrate fascinating phenomena such as galaxy formation and the cosmic web, a vast structure resembling a tangled network filled with nodes where galaxies cluster. By visualizing the evolution of these cosmic structures over billions of years, scientists gain invaluable insights into how galaxies grow, interact, and cluster together. Moreover, simulations serve as a testing ground for scientific theories. When predictions made by a simulation match observations from telescopes or other instruments, it strengthens our confidence in our understanding of the universe. If the predictions do not align, it pushes scientists to revisit and refine their models and hypotheses. Ultimately, computer simulations transform the abstract and often intangible realm of the cosmos into more tangible, comprehensible forms. They convert complex astrophysical concepts into engaging visualizations that reveal the intricate relationships and patterns defining our outer space environment. Particle physics plays a crucial role in deepening our understanding of the universe's potential fate by shedding light on the fundamental forces and particles that govern cosmic behavior. To grasp how these tiny building blocks influence the destiny of everything, we must first acknowledge that the universe consists of matter and energy interacting through fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces. One significant concept in particle physics is the Higgs boson, often called the particle that gives mass to other particles. The properties of the Higgs field could affect the overall stability of the universe. If this stability were suddenly disrupted, it might trigger a catastrophic event known as vacuum instability. This theoretical scenario suggests that a sudden shift in the Higgs field could initiate a chain reaction of particle transformations, potentially obliterating the current universe and replacing it with a different state of reality. In addition to the Higgs boson, particle physics offers valuable insights into dark matter and dark energy. mysterious components believed to make up most of the universe. Dark matter interacts with ordinary matter primarily through gravity, playing a vital role in the structure and formation of galaxies. Dark energy, on the other hand, is thought to drive the accelerating expansion of the universe. If the balance and interactions among these forces change, it could lead to dramatically different cosmic outcomes. These range from a slow cooling process as the universe expands indefinitely to a potential big crunch, where gravitational forces might pull everything back together. Theoretical scenarios such as the heat death of the universe describe a future in which energy becomes evenly distributed across space. In this state, stars will burn out, galaxies will drift apart, and all forms of life will eventually cease to exist in an ever colder, emptier cosmos. Each of these possible endings, whether caused by vacuum instability, dark energy, or energy depletion, stems from principles illuminated by particle physics. By studying the smallest particles, we gain perspective not only on how the cosmos evolved, but also on its ultimate fate, revealing that the path toward the universe's end is as complex and mysterious as the universe itself. Interdisciplinary research plays an indispensable role in expanding our understanding of the universe's vast boundaries. By integrating knowledge from physics, astronomy, mathematics, biology, and even philosophy, scientists can approach cosmic questions from many angles, unlocking new perspectives that might be missed by any single field alone. For example, astrophysicists who study celestial phenomena collaborate with mathematicians skilled in complex algorithms to create sophisticated models simulating the behavior of galaxies or black holes on a cosmic scale. Biologists contribute insights into the potential for life under extreme conditions, sparking discussions about what forms life might take on distant planets or moons. This fusion of knowledge encourages innovative thinking. Take the exploration of dark matter and dark energy as an example. While physicists propose theories to explain these enigmatic components, insights from cosmology and particle physics help anchor these concepts in observable data, leading to more robust hypotheses about the universe's structure and fate. In this way, the combined efforts of multiple disciplines drive humanity's quest to unravel the profound mysteries of the cosmos, bringing us closer to understanding our place in the grand cosmic design. Moreover, interdisciplinary approaches have the power to challenge long-standing paradigms by introducing fresh perspectives that reshape the very foundation of scientific inquiry. Philosophers, for example, provide critical reflections that compel scientists to reconsider the fundamental assumptions behind their questions, encouraging deeper exploration of the principles guiding their work. This collaboration between fields fosters a richer, more comprehensive understanding of universal phenomena. It not only drives theoretical breakthroughs, but also sparks technological innovations that enable further discovery. By blending expertise from various disciplines, humanity pushes the boundaries of knowledge and comprehension, drawing ever closer to unraveling some of the most profound mysteries about existence and the vast cosmos. Scientific debates are vital in propelling our understanding of the universe's outermost edges, realms filled with mysteries and profound questions. These discussions often unite researchers with diverse backgrounds and viewpoints, challenging existing ideas and inspiring innovative thinking. When scientists engage in debate, they scrutinize assumptions, design groundbreaking experiments, and formulate novel theories. This process resembles a collaborative puzzle where each participant contributes pieces of knowledge and insight, gradually constructing a fuller picture of complex phenomena. Take, for instance, the ongoing debates around the universe's elusive boundaries, such as dark matter and dark energy. Researchers hold differing opinions about their nature and influence, prompting rigorous testing and the generation of new hypotheses. Through such productive contention, improved models emerge, ready to be tested and refined. Debates also fuel technological and methodological innovation, empowering scientists to collect data once deemed unreachable. Like all scientific endeavors, the exchange of ideas sharpens individual thinking and propels the entire field forward. When these debates capture public interest, they broaden engagement with the scientific process, often leading to increased funding, more research opportunities, and heightened enthusiasm for science education, all of which accelerate discoveries at the edges of the known universe. Through constructive argument and cooperation, scientific debates create fertile ground for breakthroughs that illuminate the cosmos and deepen our understanding of the unknown. Sharing data across disciplines unlocks vast stores of insight, often leading to unexpected discoveries and progress. Each scientific field, whether biology, physics, or astronomy, operates with its own unique methods and principles. By opening the doors to interdisciplinary data, scientists gain fresh perspectives that reveal patterns and connections hidden within the confines of their specialties. One key takeaway from this practice is the immense power of collaboration. Diverse viewpoints ignite creativity, allowing researchers to combine their expertise to tackle complex challenges. For example, understanding climate change benefits from the combined efforts of ecology, geology, and atmospheric sciences. Together, they build comprehensive models that incorporate numerous environmental factors, resulting in more effective solutions. Interdisciplinary data sharing also uncovers new questions and challenges, pushing scientists to expand their research horizons. Unforeseen variables or phenomena may arise, demanding broader inquiry and the formulation of innovative hypotheses. Insights from genetic research, for instance, can influence medical practice, while discoveries in neuroscience might shape advancements in artificial intelligence. Moreover, openly sharing data promotes transparency and reproducibility, essential pillars of scientific integrity. When studies are accessible, they foster a culture of trust and accountability, enabling others to verify and build upon findings, reinforcing the cumulative nature of knowledge. Ultimately, embracing interdisciplinary collaboration enriches scientists' understanding not only of their immediate subjects, but also of the intricate interconnectedness that binds various scientific fields. This spirit of cooperation drives progress and deepens humanity's collective comprehension of the universe. The partnership between astronomers and physicists exemplifies this dynamic, playing a crucial role in reshaping our understanding of the cosmos. Though distinct, these fields intersect profoundly in their quests to unravel celestial mysteries. Astronomers focus on observing phenomena, gathering data about galaxies, stars, and cosmic structures. Physicists, meanwhile, seek to decode the fundamental forces and laws that govern these observations through theoretical models. By working together, they merge observational evidence with conceptual frameworks to form a more complete cosmic narrative. For instance, physicists develop theories about fundamental particles and forces, which astronomers then test and challenge through their observations. When astronomers detect unexpected patterns, such as anomalies in planetary motion or the universe's expansion, physicists reevaluate existing theories about gravity or spacetime's fabric. This ongoing dialogue between theory and observation has fueled groundbreaking discoveries, including the detection of gravitational waves. These ripples in spacetime, produced by massive cosmic events, were predicted by physicists through Einstein's general relativity. Astronomers' observations not only confirmed this prediction, but also opened a new window for studying the universe, allowing scientists to observe phenomena previously hidden from view. Furthermore, the collaboration across different scientific fields often sparks fresh questions and opens new paths for exploration. A prime example of this dynamic is the ongoing investigation into dark matter and dark energy. Though invisible to our instruments, astronomers detect these mysterious components through the subtle influences they exert on galaxies and the large-scale structures of the cosmos. This observational evidence drives physicists to develop theoretical models that could explain their true nature. The interplay between observational astronomy and theoretical physics creates a fertile ground for innovation, demonstrating that our understanding of the universe is constantly evolving rather than fixed. This continuous exchange between astronomers and physicists fosters a richer conversation about the cosmos. It allows for more refined perspectives and accelerates scientific breakthroughs. This synergy perfectly illustrates how the pursuit of knowledge thrives when diverse viewpoints come together, ultimately deepening our comprehension of the universe and our place within it. Looking ahead, several groundbreaking missions and advanced technologies are poised to push the frontiers of space exploration even further. Among these, the James Webb Space Telescope stands out as one of the most eagerly awaited projects. Equipped with powerful instruments, it will peer deeper into space and further back in time than any telescope before it. Its mission includes studying the birth and evolution of stars and galaxies, examining distant exoplanets, and potentially identifying the chemical building blocks that might support life elsewhere in the universe. In parallel, the European Space Agency is preparing the Euclid mission, designed specifically to unravel the secrets of dark energy and dark matter. These enigmatic forces make up the majority of the universe's content, yet remain largely mysterious. By mapping billions of galaxies, Euclid aims to reveal how these forces influence the universe's structure and ongoing expansion. Human space exploration is also set for a significant leap forward with NASA's Artemis program, which plans to return astronauts to the moon. This initiative will establish a sustained human presence on the lunar surface and serve as a testbed for technologies vital for future missions to Mars. These include advancements in life support systems, habitat construction, and sustainable resource management, all crucial for long-duration space travel to more distant destinations. On a more experimental front, numerous robotic missions are lined up to explore the outer planets and their moons. NASA's Europa Clipper, for example, will closely study Europa, one of Jupiter's moons believed to harbor a subsurface ocean with conditions that could support life. Cutting-edge technologies like space-based laser propulsion could transform space travel itself by using powerful beams of light to propel spacecraft faster and more efficiently than conventional rockets, enabling missions that reach far deeper into the solar system and beyond. Together, these efforts not only mark the next steps in humanity's quest to understand the cosmos, but also reflect our enduring curiosity and determination to explore the unknown. Each mission brings us closer to answering profound questions about the universe and our place within it. The new generation of telescopes represents a monumental leap forward in our ability to study the universe and its vast boundaries. These advanced instruments will employ state-of-the-art technologies to capture light from some of the faintest and most distant cosmic objects. Imagine gazing into the night sky, not only in visible light, but also uncovering hidden information carried in infrared and ultraviolet light. This expanded range will allow astronomers to study celestial bodies typically hidden or too far away to observe with current telescopes. One of the most thrilling capabilities of these new telescopes is their power to analyze exoplanets, planets orbiting stars beyond our solar system. Using sophisticated imaging and spectroscopic methods, scientists will be able to detect and characterize the atmospheres of these distant worlds. This breakthrough could offer critical insights into the possibility of life elsewhere and reveal environmental conditions on planets light years away. Moreover, these telescopes will operate in large arrays that deliver far greater detail than ever before. This enhanced resolution means we can observe galaxies that formed shortly after the Big Bang, piecing together how the universe evolved over billions of years. The light reaching us from these ancient galaxies carries valuable information about their formation processes and the fundamental physics that shape them. As our observational capabilities extend, these powerful instruments will also help map dark matter and dark energy, the two most elusive constituents of the universe. Though invisible, these forces govern the structure of everything we see, yet their true properties remain largely unknown. By observing their effects on surrounding galaxies, astronomers hope to uncover clues about the universe's expansion and its ultimate destiny. Ultimately, the next generation of telescopes will not only expand our understanding of the cosmos's edges, but also deepen our knowledge of fundamental questions about matter, energy, and humanity's place in the grand scheme of things. With these extraordinary eyes turned skyward, we stand on the brink of discoveries that could fundamentally reshape our view of the universe. Quantum computing holds remarkable potential to revolutionize our understanding of the cosmos in several transformative ways. At its essence, quantum computing leverages the principles of quantum mechanics, enabling it to process extraordinarily complex calculations far more efficiently than traditional computers. This capability is particularly vital in astrophysics, where phenomena often involve intricate interactions and enormous data sets. One promising advancement lies in the simulation of quantum systems. Traditional models of particle interactions often rely on approximations that limit their accuracy. Quantum computers can model these systems directly, providing unprecedented insights into fundamental forces in particles. By accurately replicating conditions from the early universe or extreme environments like black holes, scientists can rigorously test physics theories in ways previously impossible. Additionally, quantum computing could dramatically enhance the analysis of massive datasets generated by telescopes and detectors. In research areas such as dark matter and dark energy, where data volumes are immense, quantum algorithms may improve pattern recognition and anomaly detection. This could reveal hidden signals and correlations that classical computers struggle to find, unlocking new discoveries about the universe's deepest mysteries. Quantum communication holds an extraordinary promise. It could transform how data is securely transferred between distant observatories scattered across the globe. Imagine researchers sharing their invaluable discoveries without fear of interception or tampering. These unbreakable, secure connections would open doors to unprecedented global collaborations, uniting the brightest minds around the world. Together, they could push the boundaries of our understanding of cosmic phenomena that have puzzled scientists for generations. In addition, advances in quantum algorithms stand to revolutionize how we tackle the complex challenges of gravitational physics and cosmology. These algorithms, designed to process higher dimensions and intricate mathematical structures intrinsic to the universe, might allow us to solve problems far faster than ever before. Quantum computers could become powerful tools for probing the very fabric of space-time, exploring groundbreaking theories that aim to unify nature's fundamental forces, a goal that has eluded physicists for decades. As quantum computation progresses, it promises to redefine our approach to the universe's deepest mysteries. By unlocking insights that remain out of reach for the most advanced classical methods, this technology could reveal secrets hidden in the cosmic tapestry. At the same time, artificial intelligence and machine learning are quietly transforming how we explore the cosmos. These technologies serve as powerful assistants to scientists, enabling them to analyze enormous volumes of data generated by telescopes and space missions. Where a human might take years to sift through millions of images and datasets, AI can do it in moments. It identifies patterns and anomalies that might otherwise go unnoticed, revealing celestial objects ranging from distant galaxies to the faintest signs of potentially habitable exoplanets. One of the most thrilling applications is in the search for gravitational waves, tiny ripples in space-time caused by cosmic collisions like merging black holes or neutron stars. Detecting these subtle signals requires scrutinizing minute changes buried in vast amounts of data. Machine learning algorithms rapidly filter out noise and highlight significant events, allowing scientists to catch these cosmic whispers with unprecedented speed and accuracy. Beyond detection, AI assists in classifying a wide variety of astronomical phenomena. It can recognize different types of stars or categorize supernovae by learning from existing data and continuously improving. This capability is crucial because the universe is constantly revealing new kinds of celestial events, and AI models adapt quickly to these ever-changing cosmic realities. In the quest to understand dark matter and dark energy, AI models simulate how galaxies interact across immense spans of time and space. These simulations help researchers grasp the invisible forces shaping our universe, offering clues to its ultimate fate. AI's role is not limited to analysis. It also enhances predictive modeling. Scientists can forecast cosmic events or estimate where new celestial bodies might be discovered, guiding observations and experiments to make the best use of limited resources. In essence, the fusion of artificial intelligence and machine learning with cosmic research accelerates discovery and deepens our understanding of the universe's fundamental workings, reshaping how we explore the cosmos. Meanwhile, the private sector is dramatically changing the landscape of space exploration. Traditionally, this realm belonged mainly to government agencies, but private companies are now bringing fresh energy, innovation, and agility. Their involvement is reshaping how humanity pursues universal discoveries. One of the key contributions of private industry is increased investment in research and cutting-edge technology. These companies often have access to resources that allow them to develop advanced spacecraft propulsion systems and scientific instruments, areas that may be limited by government budget priorities. This infusion of funding fuels innovation and technological breakthroughs that expand our capabilities in space. Unlike many government programs, private firms operate with remarkable flexibility. They can rapidly prototype and deploy missions, adapting swiftly to new scientific priorities or emerging opportunities. This agility enables a more dynamic approach to space exploration, responding quickly to unexpected discoveries or challenges. Partnerships between private companies and governmental agencies are becoming more common, combining expertise and sharing risks on ambitious missions. These collaborations lead to better data collection, analysis, and sharing, fostering a culture of discovery that benefits all of humanity. Commercial space travel also opens the door for broader participation in exploration efforts. When more people get involved, diverse ideas and approaches emerge, driving innovation and amplifying the potential for groundbreaking discoveries. The ambitions of private companies extend far beyond near-Earth activities. They are spearheading missions to Mars and beyond, and even planning asteroid mining projects. These ventures could uncover new materials and provide valuable insights into the solar system's evolution, reshaping our understanding of the universe. This synergy between private enterprise and scientific research accelerates discovery and broadens the horizons of human knowledge. Together, they weave a richer, more complex tapestry of the cosmos. At the heart of this exploration is the search for extraterrestrial life, a quest that touches on the profound question, are we alone in the universe? Scientists are pushing past the familiar boundaries of our solar system and exploring the farthest reaches of the observable universe in search of clues. A critical focus of this search lies in studying exoplanets, worlds orbiting stars beyond our sun. These distant planets vary widely in size, composition, and distance from their stars, prompting researchers to ask if any could support life. The edge of the universe matters deeply here, as new astronomical technologies allow us to observe galaxies once thought unreachable. These distant observations help identify potentially habitable zones where conditions such as temperature and the presence of liquid water might resemble those on Earth. Each discovery, each technological leap, brings us closer to understanding our place in the cosmos and answering one of humanity's oldest questions. The journey to uncover life beyond our planet is as much about expanding our knowledge of the universe as it is about discovering ourselves. Additionally, our understanding of how life might arise has dramatically expanded due to groundbreaking discoveries at the very edges of the cosmos. For example, extremophiles, organisms that thrive in Earth's harshest environments, send a powerful message that life can endure conditions once thought entirely uninhabitable. This revelation widens the scope of our search for life beyond our planet, encouraging scientists to consider a far broader range of extraterrestrial environments. These could include icy moons orbiting massive gas giants or the dense, swirling atmospheres of distant gas-rich planets, located even near the outermost edges of the universe. The concept of cosmic evolution plays a crucial role in this exploration. By studying the birth and growth of galaxies on the universe's frontier, researchers gain valuable clues about the chances that life might emerge as a natural consequence of how stars and planets form. Stars are more than just dazzling points of light. They create the necessary conditions for complex chemical reactions, which in turn lead to the formation of organic molecules essential for life. Understanding how these processes take place over the universe's vast timeline helps us piece together where and how life could potentially develop in the cosmos. Furthermore, the quest to find extraterrestrial intelligence is deeply intertwined with our studies of the universe's boundaries. Scientists deploy cutting-edge technology, including some of the most powerful telescopes ever built, to listen for signals from distant civilizations. These efforts reflect not only our scientific curiosity, but also a profound human longing to connect with other sentient beings who might dwell at the farthest reaches of space. This journey is as much about existential discovery as it is about gathering data. As we push the frontiers of space exploration, the knowledge gained from studying the universe's edge significantly enriches our search for alien life. It shapes a deeper understanding of the cosmos and our unique place within it. Scientists continuously explore phenomena that lie beyond our current ability to observe directly. One of the most promising breakthroughs in recent years has been the study of gravitational waves. These ripples in the fabric of space and time, created by colossal cosmic events like merging black holes or colliding neutron stars, provide an entirely new way to observe the universe. When detected, gravitational waves reveal hidden details about these cataclysmic events, insights that traditional telescopes simply cannot offer. In addition to gravitational waves, researchers are investigating the mysterious dark matter and dark energy, which together make up the vast majority of the universe's mass energy content. Though these phenomena remain invisible and undetected through direct observation, scientists employ advanced experiments and observational strategies to infer their nature. For example, projects like the Large Hadron Collider aim to discover the properties of dark matter particles, while wide-field sky surveys work to understand how dark energy influences the accelerating expansion of the cosmos. Another exciting frontier lies in high-energy astrophysics. Space-based observatories that capture X-rays and gamma rays allow scientists to study some of the universe's most extreme events, such as powerful gamma-ray bursts or enigmatic neutron stars. These observations offer vital clues about the fundamental forces and processes that govern cosmic evolution. The search for exoplanets continues to hold tremendous promise as well. By using techniques like transit measurements, where a planet passes in front of its host star, or direct imaging, astronomers are discovering distant worlds that might possess the right conditions to support life. Each new find broadens our knowledge of planetary systems far beyond our own solar neighborhood. Technology plays a key role in all these advancements. Next-generation telescopes and satellite missions will soon revolutionize our view of the cosmos. As these instruments come online, they are expected to reveal phenomena that have so far remained hidden, fundamentally reshaping our understanding of the universe. Together, these diverse avenues are setting the stage for discoveries that may redefine what we know about the cosmos and what lies beyond the familiar. Breakthroughs in propulsion technology could be transformative for space exploration, enabling journeys to distant stars or even other galaxies within a single human lifetime, something previously thought impossible. Advanced propulsion systems work by ejecting particles at incredible speeds, producing thrust far more efficient than traditional chemical rockets. Concepts such as ion propulsion or the theoretical nuclear thermal propulsion could enable spacecraft to travel vast distances with heavier scientific instruments on board. This means that in the near future, we could explore regions of space once deemed unreachable, gathering data from celestial bodies and cosmic phenomena that have remained out of our grasp until now. In essence, the fusion of cutting-edge technology and cosmic exploration is opening doors to a universe rich with mysteries. Each step forward deepens our understanding of the origins of life, the workings of the cosmos, and our own place within this vast and awe-inspiring expanse. Moreover, advancements in propulsion technology have the potential to revolutionize the search for extraterrestrial life. By dramatically increasing mobility, these technologies could enable missions to distant moons and planets within our own solar system. Places like Europa, with its icy surface and hidden ocean, or Mars, with its intriguing history of water and potential habitability. If we can travel to these locations more quickly and efficiently, our ability to collect samples and perform detailed experiments would improve by leaps and bounds, allowing us to gain insights that were once thought impossible. Delving deeper, understanding the physics that underpin advanced propulsion systems could open new windows into the fundamental laws that govern the universe. Concepts such as warp drives or other mechanisms that suggest faster-than-light travel challenge the very framework of space and time as we currently understand it. Investigating these ideas could uncover unexpected aspects of relativity and quantum mechanics, broadening our grasp of scientific principles that define reality itself. These propulsion breakthroughs would not only push the boundaries of exploration, enabling us to reach the farthest corners of the cosmos, but also transform our theoretical frameworks. By reshaping what we know about the universe, they would ultimately change how we perceive our place within it. Through these developments, humanity would not simply observe the stars from afar. We might begin to unlock the very secrets they hold. Scientists envision a future where international collaboration becomes the backbone of space exploration. Given the immense vastness of space and the enormous challenges involved, no single nation possesses all the necessary resources or expertise to venture far beyond Earth on its own. Imagine a global network of space agencies, research institutions, and private companies joining forces to share knowledge and technology. This united front could lead to ambitious joint missions, such as international efforts to explore Mars, where experts from around the world collaborate on everything from landing technologies and rover designs to sustainable life support systems. Such cooperation would not only maximize the scientific returns of each mission, but also promote peaceful relations and common goals among nations. Beyond planetary exploration, international partnerships could extend to astronomical observation. Countries might establish observatories across the globe, working together to monitor cosmic events like supernovae or discover new exoplanets. This collective approach would bring together the best minds from diverse backgrounds to tackle fundamental questions about the universe, from the elusive nature of dark matter to the possibility of life beyond Earth. These collaborative efforts could also address the practicalities of human settlement beyond our planet. By pooling resources and expertise, nations could develop the technologies required for sustainable living and resource management on other worlds, whether on distant planets or even asteroids. Over time, this spirit of cooperation might usher in a new era of exploration, where humanity collectively clears a path for future generations to journey beyond our solar system, sharing both the risks and the wonders of the cosmos. At the heart of this exploration lies education and outreach, powerful catalysts that inspire the next generation of explorers, introducing young minds to the vastness of space, the complex workings of celestial bodies, and the challenges of space travel through engaging activities and interactive lessons sparks curiosity and wonder. Programs that allow children and teenagers to build scale models of planets or simulate rocket launches make science tangible, transforming abstract ideas into concrete experiences. When students watch a model rocket soar or see a simulated rover traverse the Martian surface, they connect deeply with the concepts behind these phenomena. This hands-on learning fosters enthusiasm and critical thinking, motivating them to explore science and technology further. Storytelling also plays a vital role in outreach efforts. Tales of pioneering astronauts, groundbreaking scientists, and thrilling discoveries capture imaginations and show young people that they too can be part of this grand adventure. Incorporating diverse voices in these stories ensures that students from all backgrounds see themselves reflected in the journey of space exploration. Access to mentors, scientists, and engineers who share their knowledge and inspire confidence is equally crucial. These role models demonstrate that anyone, regardless of origin, can contribute meaningfully to advancing our understanding of space. Through effective education and outreach, we nurture a culture where curiosity thrives, igniting passion for science, technology, engineering, and mathematics. This supportive community empowers the next generation to become the explorers and innovators of tomorrow. The universe is vast and filled with mysteries, and with the right encouragement, today's youth will grow into tomorrow's pioneers, uncovering secrets yet to be revealed. Gazing toward the edges of the cosmos captivates and transforms human culture in profound ways. The quest to understand what lies beyond our familiar world fuels imagination and inspires creativity across many fields. When we look out into space, we do more than observe distant galaxies or cosmic phenomena. We reflect on our own existence. Questions about our origins and destiny challenge us to rethink our values, philosophies, and relationships with one another. Discoveries at the universe's edges resonate deeply with humanity, sparking stories of exploration, wonder, and the eternal search for knowledge. Artists, writers, and filmmakers draw from these cosmic themes, weaving narratives that touch on existential questions and the possibilities of life beyond Earth. Science fiction thrives in this rich landscape, encouraging audiences to envision future technologies and societies shaped by interstellar travel and the boundless frontier beyond our world. Additionally, the breathtaking images unveiled through telescopes and space missions ignite a shared sense of achievement that transcends borders. These mesmerizing views of dazzling nebulae and the vast, seemingly endless universe remind us all that we are part of a collective journey as a species. This shared cosmic perspective encourages a profound sense of unity and responsibility, urging humanity to work together in caring for our fragile planet while simultaneously reaching outward toward the stars. As researchers relentlessly push the limits of what we know, an increasingly diverse group of people finds inspiration in science and technology. This growing curiosity nurtures a culture that values inquiry, innovation, and critical thinking, encouraging a deeper appreciation for the quest to understand the universe's farthest edges. The drive to uncover answers transforms education, motivating young minds to explore fields like science, engineering, and the arts, propelling society forward in unexpected and exciting ways. Our exploration of the universe's boundaries serves not only as a scientific endeavor, but also as a powerful catalyst for cultural transformation. It fosters a sense of wonder and interconnectedness that resonates through art, philosophy, and the shared human experience. Peering into the cosmos invites profound questions that go beyond scientific curiosity. When we contemplate the universe's edges, we begin to ponder the very nature of existence itself. What lies beyond those boundaries? Does anything exist there at all? These questions invite us to reflect on the essence of reality, whether the universe and all within it are the only tangible parts of existence, or if there might be something greater, perhaps an infinite realm beyond our comprehension. Further contemplation turns to the nature of time and space. If the universe indeed has limits, what does that mean for our understanding of time? Could time itself have a beginning and an end? Such considerations shape how we perceive our own existence within this vast cosmic expanse. This line of thought leads to questions about the universe's origin. What sparked it into being? What does that say about cause and effect on the grandest scale? Moreover, examining these cosmic boundaries invites reflection on human significance and our place in the vast cosmos. Are we simply tiny specks of dust floating in an immense void? Or does our consciousness and capacity for thought play an integral role in a larger cosmic plan? This question challenges us to think deeply about life's purpose. If the universe is boundless, do we hold greater importance in unraveling its mysteries? Or are we merely observers within an indifferent system? Finally, exploring the structure of the universe raises important ethical questions. How should we conduct ourselves in relation to the cosmos and to one another? Are there moral responsibilities tied to our actions on Earth and beyond, especially as we consider the possibility of life elsewhere in space? These philosophical reflections, sparked by the study of the universe's limits, compel us to examine not only the stars but also our own humanity. Understanding the boundaries of the universe profoundly reshapes our view of Earth and our place within the cosmos. When we study the universe's vastness, its immense age, and the fundamental laws governing its behavior, we begin to appreciate the delicate balance and fragility of our own planet. Earth is far more than just a home. It is an extraordinary oasis of life within an overwhelmingly vast and mostly inhospitable universe. As we learn that the universe extends far beyond what we can see, reaching into infinite distances, we realize how tiny our planet truly is within this grand cosmic landscape. This awareness deepens our awe for the rare conditions that allow life to flourish here. Earth's atmosphere, the presence of liquid water, and a perfect temperature range are not just fortunate circumstances, they are extraordinary exceptions in the universe's extreme environment. Discoveries about cosmic events, such as the life cycles of stars and phenomena like supernovae, highlight the deep interconnectedness of everything in the universe. We are reminded that the very elements forming our bodies were forged in the cores of ancient stars, linking us to the vast cosmic processes far beyond our planet. This perspective can help soften human conflicts by emphasizing our shared existence and collective responsibility toward each other and our environment. Furthermore, understanding the universe's limits raises urgent questions about sustainability and the finite nature of Earth's resources. Recognizing these physical limits inspires a more conscientious approach to how we live, sparking efforts in conservation and innovation. Humanity is urged to protect this beautiful blue planet, not only for ourselves, but possibly for all life as we know it in the universe. Far from diminishing our significance, this deeper knowledge of the universe's boundaries uplifts us. It calls us to become stewards of Earth while fostering a profound appreciation for the extraordinary conditions that make life possible. Space exploration captivates human imagination unlike almost any other pursuit. It represents the ultimate quest for knowledge, constantly pushing the frontiers of what we understand about ourselves and the universe around us. When we gaze up at the night sky, we see not only stars, but endless potential for discovery and connection with worlds beyond our own. This quest has stirred deep curiosity throughout human history, prompting us to wonder if we are alone in the cosmos and what mysteries await beyond our planet. Each mission, from landing on the moon to exploring Mars or capturing breathtaking images of distant galaxies, transforms curiosity into concrete achievement. Together, these journeys weave a powerful narrative, combining science, engineering, and the indomitable human spirit of adventure. They inspire generations to dream bigger, pushing humanity literally and metaphorically to reach for the stars. Moreover, the images captured and discoveries made through space exploration ignite a profound sense of awe and wonder. These revelations compel humanity to reflect on fundamental questions about existence, what life truly is, where we stand in the vast cosmic landscape, and what the future holds for us as a species. Each mission sparks conversations that reach far beyond technology. They touch upon cooperation among nations and the tantalizing possibility of encountering life beyond Earth. Every journey into space serves as a powerful reminder of our shared dreams and challenges, fostering a deep sense of unity amid the immense and seemingly endless universe. Space exploration transcends mere scientific pursuit. It embodies human ambition, resilience, and creativity, enriching the cultural fabric of societies worldwide and planting seeds of hope for what lies ahead. It suggests that beyond the boundaries of our current knowledge exists an infinite horizon, teeming with potential discoveries waiting patiently to be unveiled. These discoveries, particularly those at the edge of the universe, have the potential to radically reshape how we perceive existence itself and our place within the cosmic order. At the forefront of these explorations, revelations may emerge that uncover the structure and ultimate fate of the universe. They may answer whether the universe is finite or infinite, a question that profoundly impacts both philosophical contemplation and scientific inquiry. Such insights could lead humanity to reevaluate its role in the cosmos, prompting new reflections about life and our collective destiny. Furthermore, gaining a clearer understanding of dark energy, the mysterious force driving the universe's expansion, could allow us to predict the long-term fate of galaxies, stars, and even our own solar system. Whether the cosmos is accelerating outward at an ever-increasing pace or destined to contract in a cosmic reversal, these scenarios would influence humanity's long-term strategies for survival. This knowledge might fuel the development of advanced technologies designed to ensure our species' continuity, perhaps even on other celestial bodies. Discoveries at the universe's edge could also catalyze revolutionary advances in technology. Studying extreme cosmic phenomena, such as matter subjected to intense gravitational forces near black holes, could inspire innovations in energy generation, material science, and computing. These breakthroughs might empower us to harness energy with unprecedented efficiency, or develop new methods of space travel, vastly extending our capacity to explore regions far beyond our immediate cosmic neighborhood. The revelations emerging from our cosmic explorations could unify humanity under a shared purpose. The inspiration drawn from venturing into the unknown could ignite a collective ambition to transcend our earthly limitations, fostering international cooperation in scientific pursuits. As we deepen our understanding of the universe, the interconnectedness of all life becomes more apparent, nurturing a greater appreciation for the delicate balance sustaining our home planet within the vastness of space. Ultimately, the voyage to understand the universe's edge could redefine not only our scientific and technological ambitions, but also our identity as a species. It weaves together the diverse experiences of humanity into a common narrative of exploration, discovery, and an insatiable thirst for knowledge, one that may even transcend the stars themselves. Unlocking the secrets of the cosmos significantly shapes the trajectory of scientific endeavors. Breakthroughs in understanding dark matter or the nature of black holes spark renewed curiosity and set new directions for research. These discoveries open fresh questions demanding attention, causing scientists to prioritize investigations that once seemed less urgent. For example, a better grasp of the universe's origins might redirect focus toward unraveling the fundamental laws of physics that govern reality. Researchers could channel efforts into particle physics or high-energy astrophysics, conducting experiments probing the very fabric of existence. Similarly, insights into exoplanets and their atmospheres might elevate the search for extraterrestrial life, advancing fields like astrobiology and planetary science. In this way, every discovery expands our horizon, shaping not only what we know, but how we seek to know more. Moreover, cosmic discoveries have far-reaching impacts beyond just expanding our knowledge of the universe. The very tools and technologies developed for exploring space often find unexpected and practical applications here on Earth. This dynamic relationship between space research and earthly innovation fuels progress in various fields such as engineering, data science, and environmental research. As we unravel the mysteries of the cosmos, the excitement generated by confirming theories or revealing new cosmic phenomena invigorates not only astronomy, but a broad spectrum of scientific disciplines. This energy helps direct funding and resources into diverse areas, inspiring further exploration where human curiosity seeks to grow. Each breakthrough in understanding the universe offers us a wider lens through which to view our place within it. It prompts us to reconsider what questions are most urgent to answer and what technologies or strategies will best advance our quest for knowledge. Every discovery nudges us toward new questions, creating a constantly evolving landscape of scientific priorities shaped by our deepening grasp of the cosmos. Historically, how humanity has interpreted the universe's limits has greatly influenced modern scientific inquiry. In ancient times, many civilizations imagined the universe as a fixed, Earth-centered system, where our planet was thought to be the center of all existence. Stars and planets were believed to move in perfect circles around Earth, limiting the scope of human understanding. However, as observational tools improved and revolutionary thinkers like Nicholas Copernicus introduced the heliocentric model, proposing that planets orbit the sun, our conceptual boundaries expanded dramatically. Moving into the 20th century, the invention of more powerful telescopes revealed that our galaxy, the Milky Way, was just one among countless others. This revelation fundamentally transformed our perception of the universe's vastness. Then came Edwin Hubble's discovery of the expanding universe, overturning the previous idea of a static cosmos and opening the door to questions about its origins. This led to the development of the Big Bang theory, which suggests that the universe began as a single, incredibly hot and dense point before expanding. Today, these historical milestones form the foundation of ongoing research. Scientists investigate dark matter and dark energy, mysterious substances believed to drive the universe's accelerating expansion, building directly upon past models. We now understand that cosmic limits are not fixed barriers, but evolving concepts that shift as our knowledge grows. Researchers employ advanced technology like powerful telescopes and particle accelerators to probe the universe's edges, seeking to uncover its composition and ultimate fate. Reflecting on these historical interpretations reminds us that every major breakthrough deepens our appreciation for our cosmic context. They highlight the need to remain open to new discoveries that could forever change our understanding of the universe's boundaries. The pursuit to explore not only the farthest reaches of space, but also the fundamental laws that govern it continues to evolve, propelled by lessons learned from the past. Throughout history, humanity's journey into the cosmos has sparked a rich tapestry of cultural narratives, reflecting our hopes, fears, and aspirations. The vastness of space, once a realm of myth and wonder, has become the backdrop for stories that challenge our understanding of existence. From ancient civilizations looking to the stars for meaning, to modern science fiction exploring technological progress and alien life, cosmic exploration has profoundly influenced storytelling. One common narrative portrays humanity as explorers venturing bravely into the unknown. As we develop the technology to travel beyond Earth, stories emerge of astronauts facing incredible wonders and terrifying uncertainties. These tales, found in films and literature, explore themes of isolation, the fragility of life in space, and the search for meaning amid the cold, vast cosmos. Such stories resonate deeply because they evoke our own fears of the unknown and our relentless desire to discover. Another powerful cultural narrative revolves around the search for extraterrestrial life. This quest has inspired countless stories, questioning what it would mean to find intelligent beings beyond Earth. These stories challenge our understanding of life, ethics, and civilization, prompting us to reflect on humanity's nature and how we relate to other forms of life. They imagine encounters that could transform our worldview, sparking dialogue about coexistence, communication, and the complexities of sharing the universe. Exploring cosmic boundaries has also influenced philosophical thought on existence and destiny. The immense scale of space provokes profound questions about our purpose and fate. These themes appear across literature and film, where characters confront their limitations and the grand forces shaping reality. Such narratives encourage us to consider our destiny in the universe and the legacy we hope to leave behind. As humanity pushes the boundaries of space exploration, whether through robotic missions to distant worlds or plans to send humans to Mars, these cultural stories continue to evolve. They inspire new generations to ponder not only what lies beyond our planet, but also what it means to be human in an enormous, mysterious universe. Each journey into the cosmic unknown reshapes both our understanding and our storytelling, becoming a reflection of our collective consciousness and our intertwined fate with the cosmos. As scientific knowledge expands, so too do the worldviews shaping how individuals see their place in the universe. Initially, many people interpreted the cosmos through myths, legends, and religious beliefs, where celestial events were often attributed to divine actions. These narratives have offered comfort by explaining mysteries like the changing seasons or the movement of stars. However, as science revealed natural laws, the heliocentric model challenged the idea of Earth as the universe's center. This revolutionary insight ignited a more questioning mindset. Discoveries such as the laws of gravity and the nature of light demonstrated that rational explanations could be found for many phenomena. As astronomy, cosmology, and physics advanced, individuals began to grasp that the universe is unimaginably vast and full of secrets yet to be uncovered. The possibility of life elsewhere in the cosmos became more plausible, leading to profound shifts in perspective. Instead of feeling isolated on a small planet, many now appreciate being part of a vast, interconnected cosmic tapestry, a single thread woven into the grandeur of the universe. Moreover, as scientific advancements gradually unveil the grand narratives of the cosmos, like the birth of stars, the evolution of entire galaxies, and the fundamental laws that govern all matter, our understanding of human significance undergoes a profound transformation. Concepts such as the Big Bang, which describes the origin of the universe, and the relentless expansion of space itself, challenge the way individuals perceive their place within the vast cosmos. People often find themselves wrestling with feelings of both insignificance and a deep, extraordinary connection to everything that lies beyond our immediate experience. This expanding worldview does more than reshape our intellectual grasp of reality. It deeply influences our emotional and philosophical outlooks as well. As scientific literacy becomes more widespread, there is a noticeable shift in how people approach questions about existence. Instead of relying solely on tradition or rigid belief systems, many start to value evidence-based reasoning. This movement towards inquiry and skepticism nurtures curiosity and sparks a desire to explore the unknown. Such a mindset cultivates an inquisitive spirit, one that prizes discovery and the ongoing search for knowledge. While this perspective can be intimidating to some, it also inspires awe and wonder. Viewing existence through a scientific lens reveals the intricate complexity and elegance of the universe, encouraging a profound appreciation for the delicate balance and interconnectedness of all things. As humanity's collective understanding deepens, so too does the complexity of our worldviews. Each new scientific discovery acts like a vital piece of a cosmic puzzle, helping individuals reconstruct their sense of existence in ways that blend empirical insight with personal meaning and purpose. The pursuit of universal knowledge does not merely shape intellectual thought, it fundamentally influences ethical considerations here on Earth. This creates a delicate interplay between the excitement of exploration and the responsibility we bear toward one another and the planet. As we venture into the vast unknown, driven by the desire to understand our origins, the nature of reality, and the possibility of life beyond Earth, we are compelled to reflect on how these revelations affect our moral compass and social values. For example, technological advances stemming from space exploration have the potential to improve life on Earth. However, they also introduce difficult ethical questions, such as who should have access to these transformative technologies. Without careful attention, innovations can deepen existing inequalities if benefits are concentrated among a privileged few. Thus, balancing the thrill of discovery with a commitment to fairness and equity becomes a crucial challenge. Moreover, the potential discovery of extraterrestrial life, whether microbial organisms on distant planets or more complex beings, raises new ethical dilemmas. How do we honor and protect life beyond Earth without compromising human exploration and ambition? These questions demand an ethical framework that respects all forms of life and encourages us to act with foresight, caution, and care. As we uncover universal truths, we must also reconcile them with the rich tapestry of cultural beliefs and values found around the world. The quest for knowledge can sometimes clash with traditional worldviews, sparking ethical tensions that call for open dialogue and mutual respect. The knowledge we gain should serve to foster collaboration and inclusivity, not division or conflict. Ultimately, the pursuit of universal knowledge acts as a catalyst for profound reflection on our responsibilities, not only as cosmic explorers, but as caretakers of our planet and all its inhabitants. This ongoing journey demands thoughtful engagement with the consequences of our discoveries and encourages us to envision a future where knowledge uplifts humanity as a whole, rather than creating new divides. At the core of this journey lies an innate human curiosity about the unknown. This natural drive to explore and understand what lies beyond our immediate surroundings has shaped human culture for millennia. Since the earliest ancestors gazed at the night sky, wondering about the stars, humans have sought to unravel the mysteries beyond our world. This quest for knowledge is a fundamental force, fueling scientific inquiry and inspiring innovation. The vastness of space represents the ultimate frontier, filled with secrets that could vastly expand our understanding of existence itself. Questions about whether we are alone in the universe or what the true nature of reality is push us onward, reminding us of our fragile yet extraordinary place in the cosmos. Each discovery, from identifying faraway galaxies to understanding cosmic phenomena like black holes, adds depth to our worldview and kindles a sense of shared adventure. As we learn more about the universe, we simultaneously uncover insights about ourselves, our past, and the possibilities for our future. It is this dynamic interplay of curiosity, discovery, and self-reflection that compels us to peer deeper into the cosmos, eager to grasp what lies just beyond our reach. Scientists navigate this vast and uncertain landscape by combining creativity, rigorous experimentation, and collaborative effort. They begin by accepting the limits of current knowledge, knowing that every answer often leads to new questions rather than final conclusions. This understanding fuels their relentless quest for understanding. A key part of their approach involves developing hypotheses, educated guesses rooted in existing theories and observations. These hypotheses guide experiments and observations designed to gather new data. Whether peering through powerful telescopes into distant galaxies or smashing particles together in advanced colliders to reveal the hidden building blocks of matter, each step brings us closer to unveiling the universe's secrets. Even when results are unexpected or challenge current theories, they push science forward, opening new paths for exploration and understanding. Moreover, scientists have eagerly embraced technological advancements to extend the frontiers of their exploration. Innovations such as sophisticated sensors and advanced computational models now allow researchers to investigate realms once thought impossible to reach. For example, the arrival of powerful space telescopes has dramatically broadened our capacity to observe distant exoplanets and cosmic phenomena, shedding light on parts of the universe that have long remained shrouded in mystery. Collaboration plays a crucial role in this ongoing scientific journey. Experts from a variety of fields come together, creating an interdisciplinary dialogue that enriches their collective understanding. This spirit of cooperation encourages the sharing of knowledge and ideas, often sparking breakthroughs that would be unlikely in isolation. The cross-pollination of perspectives enhances comprehension across many scientific disciplines, enabling new discoveries to emerge. Furthermore, scientists maintain a sense of open-mindedness and adaptability. They understand that the universe often behaves in ways that challenge initial expectations. The willingness to revise theories when new evidence arises is a defining feature of scientific progress. By embracing uncertainty as a vital part of the quest for knowledge, researchers continue to push the boundaries of human understanding, turning questions into discoveries that inspire future generations. Cosmologists, in particular, face the unique challenge of conveying complex concepts about the vastness of the universe and its mysterious edges to the public. To bridge the gap between intricate scientific ideas and everyday understanding, they employ various methods. One powerful technique involves the use of analogies, which relate unfamiliar ideas to common experiences. By comparing the universe to a balloon that expands or a fabric that stretches, cosmologists help illustrate abstract notions of space and time that are difficult to grasp. Visualization also serves as a potent tool. Through detailed illustrations, computer simulations, and even virtual reality experiences, cosmologists create vivid depictions of cosmic phenomena. These visual aids allow people to witness ideas such as the curvature of space or the distribution of galaxies in ways that words alone cannot fully convey. Storytelling is another essential element in their communication efforts. By weaving narratives around the life cycle of stars, the birth of galaxies, or the enigmatic nature of dark matter, cosmologists engage audiences both emotionally and intellectually. These stories capture the essence of complex cosmic processes, making them relatable and sparking curiosity. Public lectures, documentaries, and educational outreach initiatives further serve to inform and engage wider audiences. Through these platforms, cosmologists present their findings and theories clearly and accessibly, inviting questions and discussions that deepen understanding. Collaborations with artists and communicators help translate highly technical language into visually appealing and understandable content, broadening the reach of scientific ideas. Together, through analogies, visualization, storytelling, public engagement, and creative partnerships, cosmologists illuminate the abstract concepts surrounding the universe's edge. They invite everyone to join in exploring the cosmos and its mysteries. The question of the universe's boundaries both fascinates and challenges scientists. Imagine standing at the edge of a vast, uncharted ocean where endless possibilities stretch beyond the horizon. This metaphorical edge of the universe drives researchers to ponder not only what lies beyond the limits of our observation, but also the very nature of those boundaries. The mystery of the universe's edge inspires scientists to think creatively and explore ideas that defy everyday understanding. For example, does the universe have a definite shape? Some propose it might be infinite, endlessly expanding like a balloon being inflated. Others suggest it could be curved back upon itself, resembling a sphere. Each of these hypotheses requires innovative thinking and new concepts as scientists test their ideas against the ever-growing body of data. This enigma also fosters interdisciplinary collaboration, with astrophysicists working alongside mathematicians, computer scientists, and philosophers. The blending of these diverse disciplines often leads to breakthroughs. For instance, the quest to understand dark matter and dark energy, two mysterious components believed to influence the universe's structure and expansion, demonstrates how the unknown can inspire novel approaches and experiments. The obscurity surrounding the universe's boundaries acts as a vast canvas for scientific creativity. It encourages movement beyond established theories, inviting exploration of ideas such as alternate dimensions or the multiverse. Each new question adds depth to our understanding and propels humanity deeper into cosmic inquiry, showing that the universe's mysteries are not simply puzzles to solve, but gateways to endless innovation and discovery. The pursuit of knowledge about the universe's edge has shaped the course of scientific discovery throughout history. From ancient philosophers who gazed at the stars and speculated about celestial bodies, to modern scientists mapping the cosmos, this quest reflects humanity's deep desire to comprehend existence itself. During the Age of Exploration, the limits of the Earth prompted astronomical advancements. Navigators needed to chart the skies for safer voyages, leading to the creation of instruments such as the telescope. These tools made groundbreaking observations possible. For example, Galileo's discovery of moons orbiting Jupiter challenged the long-held belief that all celestial bodies revolved around the Earth. This momentous shift moved humanity away from an Earth-centered view of the universe toward a heliocentric one. As ideas about the universe expanded, the concept of infinity began to take hold. The realization that the night sky contains countless stars, many far beyond immediate reach, inspired thinkers like Isaac Newton. Newton formulated laws of motion and universal gravitation that explained not only phenomena on Earth, but also the mechanics of celestial bodies. His work laid the foundation for further cosmic exploration, revealing that the universe follows discernible laws, guiding generations of astronomers and physicists. In the 20th century, the quest advanced dramatically with the introduction of powerful telescopes capable of detecting distant galaxies. This era brought the realization that the universe is not static but expanding. Edwin Hubble's observations showed that galaxies are moving away from one another, suggesting the universe itself is growing. This discovery led to the development of the Big Bang theory, which proposes that the universe began from an incredibly dense state. This theory radically transformed our understanding of cosmic origins and the nature of time itself. Moreover, the quest to understand the universe has consistently intertwined with the rapid progress of technology. Each major leap in our comprehension of the cosmos has often coincided with significant advancements in the tools we use to measure and observe the universe. From the first radio telescopes that detected faint cosmic radiation to the sophisticated space probes journeying to the farthest corners of our solar system, technological innovation has been directly fueled by humanity's relentless desire to see beyond what our eyes can perceive. This dynamic relationship between theoretical curiosity and practical invention illustrates how our pursuit of knowledge constantly pushes the boundaries of what is possible. Every new instrument, every improved sensor opens doors to fresh discoveries and deeper insights, allowing scientists to peel back the layers of the unknown. The journey to explore the edges of the universe is not just a scientific endeavor, but a profound expression of human curiosity and determination. Each scientific breakthrough in this grand quest serves as a stepping stone, revealing not only the vast mysteries of space, but also shedding light on our own existence within this cosmic tapestry. As researchers continue to probe the limits of the observable universe, their work weaves a vital thread into the fabric of human understanding. This ongoing pursuit shapes not only our knowledge, but also profoundly influences the psychological landscape of humanity. Our innate curiosity about the cosmos inspires a powerful sense of wonder and awe, which in turn fuels creativity and innovation. This spirit of exploration is deeply embedded in our nature, driving us to push beyond known horizons and challenge what we thought was possible. Whether it is the discovery of distant galaxies or the study of enigmatic cosmic phenomena, each revelation evokes a complex mixture of fascination and humility. The vastness of the universe often puts our own lives and concerns into perspective. It highlights both our relative insignificance in the grand scheme and our unique place within the cosmic order. This duality can foster a profound sense of connection to the universe, encouraging a deeper appreciation for life and the natural world. Yet, at the same time, the quest to understand the universe can provoke deep existential questions. As we ponder our origins and the meaning of our existence, thoughts about extraterrestrial life, the fate of our planet, and the ultimate destiny of the cosmos can stir a wide range of emotions, from hopeful anticipation to anxious uncertainty. The technical complexity and sheer scale of space research also create a powerful sense of community among those engaged in this quest. Scientists, enthusiasts, and everyday people form bonds through shared curiosity and collaboration. These connections transcend geographical and cultural boundaries, fostering a collective purpose and a shared commitment to expanding human knowledge. Ultimately, the psychological impact of humanity's quest to comprehend the universe is rich and multifaceted. It sparks imagination, challenges intellectual boundaries, and invites profound reflection on what it means to exist. Confronting the mysteries of the cosmos compels us to look inward, exploring the depths of our own human experience alongside the vast expanse of space. Artists and writers play a crucial role in this process by transforming complex scientific concepts into stories and images that resonate with a wider audience. They bridge the gap between abstract, often intimidating scientific ideas and the everyday experiences of people, making the mysteries of the universe more relatable and inspiring. When an author envisions a journey through distant galaxies or life on another world, they ignite imaginations and spark curiosity about real scientific principles. Visual art, too, brings the cosmos to life in a visceral, emotional way. Stunning depictions of galaxies, nebulae, and other celestial wonders invite viewers to contemplate their own place in the universe beyond the cold, hard facts of science. These images can evoke deep emotional responses, fostering a stronger connection to the cosmos, and inspiring further exploration of the timeless questions about existence and our role within this vast, awe-inspiring universe. Moreover, stories that intertwine scientific themes often delve deeply into profound philosophical questions about humanity, the very nature of reality, and the ethical consequences of exploring new worlds. By weaving these ideas into their work, artists and writers spark an ongoing conversation about our shared human experience and collective dreams. This dialogue pushes society to reflect critically on scientific progress and technological innovation. The fusion of art and science enriches our understanding of the universe, making its vast mysteries more accessible and inspiring a sense of awe and curiosity in everyone. Throughout history, humans have gazed at the night sky, driven by an enduring desire to unravel the secrets of the cosmos. Ancient cultures crafted myths and legends that illustrated celestial phenomena in ways deeply connected to their environments, beliefs, and hopes. Many civilizations shaped stories around star constellations, attributing to them important characters and events, heroes, animals, gods, and mythical creatures. These narratives offered a way to explain the seemingly chaotic cosmos and provided frameworks to understand natural cycles such as seasons and eclipses. What is fascinating is how modern astronomy echoes many themes found in these ancient tales. Take, for example, the myth of the celestial sea, often symbolized by the glowing Milky Way stretching across the night sky. For ancient peoples, this luminous band was imagined as a river or pathway, a symbolic journey toward the afterlife. Today, scientists describe the Milky Way as a vast spiral galaxy composed of billions of stars, each potentially hosting planets and perhaps life. This modern discovery resonates with the mythological theme of exploration and the human pursuit of immortality through knowledge. Creation stories, too, frequently involve dramatic cosmic events, like battles between divine forces or the birth of the universe from primordial chaos. These stories parallel our contemporary understanding of the Big Bang Theory, which explains that the universe began from a single incredibly dense point and has been expanding ever since. The transformation from chaos to order, so vividly told in ancient narratives, finds a striking reflection in modern astrophysics. Legends about cosmic giants or beings who shape the world also offer thought-provoking parallels. These mythical figures often symbolize elemental forces, power, creation, destruction, mirroring the real cosmic phenomena we study today. Events such as supernovae explosions and black holes hold the potential to reshape galaxies, trigger the birth of new stars, and influence planetary systems. The connection between mythological giants and the enormous natural forces we now understand illustrates humanity's enduring fascination with the universe's immense and sometimes incomprehensible processes. This rich tapestry of myths reveals humanity's relentless quest to understand our place in the cosmos. As scientific discoveries peel back layers of mystery, it becomes clear that these ancient stories still hold meaning, bridging the gap between our ancestors' insights and our current knowledge. The universe remains a boundless realm of wonder, captivating the imaginative hearts of those who came before us and the inquisitive minds of today's explorers alike. Standing at the edge of the known cosmos, where the infinite stretches beyond comprehension, invites us to reflect on our existence within this vast expanse. What does it truly mean to be part of something so grand and largely unexplored? Scientists grappling with the universe's boundaries confront profound questions about beginnings and endings. How did the universe come into being? Is there a boundary to the cosmos, or does it extend infinitely in a way that defies our understanding? These inquiries tap into a fundamental human longing to grasp the origins of existence itself. The sheer scale of the universe and the mysteries cloaking its edges prompt us to ponder our significance in an almost unimaginable setting, inviting continuous wonder and curiosity as we seek to explore and understand the vast cosmos around us. Moreover, reflecting on the universe's limits invites profound questions about the nature of time itself. If the universe indeed has an edge, what could possibly exist beyond that boundary? Could there be a reality that stretches outside the scope of our perception, something fundamentally beyond what we can observe or understand? This intersection of time and space pushes the boundaries of our comprehension of eternity, reminding us of how brief and fragile our own moments truly are within this vast expanse. The concept of an expanding universe carries with it a wave of philosophical reflections. As galaxies steadily drift apart from one another, we are compelled to confront the realities of isolation and connection on a cosmic scale. What future awaits us in this ever-expanding cosmos? Will our celestial neighborhood gradually vanish into the abyss of endless space? Such thoughts awaken a sense of urgency, not only about our personal existence, but about the collective path humanity charts here on Earth. When we study the edge of the universe, we do more than map the positions of stars and galaxies. We engage with some of the most fundamental questions humanity has ever faced. What is our purpose? What does it mean to exist? How do we find meaning in a universe that is both breathtakingly magnificent and yet profoundly indifferent to our presence? Each scientific discovery widens our horizon of knowledge, but it also deepens our understanding of ourselves and the intricate place we occupy in the grand cosmic tapestry. Our understanding of the universe is shaped by scientific paradigms, frameworks that act like lenses through which we interpret everything we observe. These paradigms guide our theories about the cosmos and its limits. When a major paradigm shift occurs, it does more than change science. It reshapes cultural views and philosophical beliefs. For example, the heliocentric model, which positioned the sun at the center of our solar system rather than Earth, completely transformed humanity's perception of its place in the universe. No longer the center of everything, Earth became one of many planets orbiting a star in a vast, almost incomprehensible space. This idea fueled the scientific revolution, sparking advances in navigation, exploration, and our understanding of gravity, all of which broadened how humanity imagined the universe. As we continue to make new discoveries, such as the expanding universe, dark matter, and dark energy, these revelations redefine the boundaries of what we thought was known. Each insight challenges previously held assumptions, compelling society to rethink the size, composition, and even the ultimate destiny of the cosmos. Recognizing that the universe extends far beyond what our instruments can detect suggests a richness that lies just outside our immediate experience, inspiring scientists and curious minds alike to explore deeper philosophical questions. These shifts in understanding are not merely abstract or theoretical, they have real-world consequences. Advances in physics and space exploration drive technological innovation that impacts industries, education, and policy decisions. As human knowledge stretches beyond previous limits, so too does our capacity to tackle urgent global challenges. Climate change, resource management, and the ethical dilemmas of new technologies among them. The dynamic relationship between evolving scientific paradigms and society's worldview influences not only how we perceive the cosmos, but also how we choose to act here on Earth.